And it's designed for 11 nines of durability. And this is just one of 100 of our services that when we think about building a key management service for how do customers encrypt their data within AWS, that we take into effect of building it for scale. So we designed KMS to be the service that allows all our customers to control the encryption of their data within AWS, providing them with separate access control mechanisms from the data itself. So in speaking to the customers, what customers really want in a key management solution is they want to know that their keys are stored in FIPS certified hardware. Records every time these keys are used to encrypt or decrypt data within AWS. And they don't really want to manage all the decisions around IV generation, key rotation, and algorithm selection. And KMS sort of handles all that for you. And I think when you look at trying to run just S3 all through a single service, it's really not feasible to load, to transmit all your data through another endpoint to encrypt it and send it back, nor is it really useful in the sense that you're just going to send it over some transport protocol to encrypt it somewhere else. And finally, the system has to have durability that's comparable to the data, the durability of the services in which we're trying to protect that data. So when we built KMS, this is sort of like a micro view of the architecture from how a customer might interact with KMS. We have the AWS KMS service that the customer interfaces with directly. And they would make a call to sort of create a key, and when they create a key, they would set a policy on that key that would specify who or what services can use that key and what APIs that can they call against that key, like changing the policy on the key or encrypting under that key or decrypting under that key. And when that occurs, the KMS service speaks to an HSM that has sort of what we call a domain key, and the HSM will generate a brand new customer master key, a 256 random bit value, and encrypt it under the domain key. And then transmit that token back to the KMS service, where it will manage the state, distribute that across the fleet of KMS servers. Later on, when a customer wants to encrypt data, they make a call to encrypt under the key ID that we return them as a lookup to that database, and they'll pass in the plain text and maybe some additional authenticated data that we call encryption context within KMS. And the KMS service will look up the EKT, the encrypted key token, and pass that back into the HSM. The HSM will just create a fresh, will decrypt that customer master key, generate a fresh random unique identifier for this encryption, derive a per encryption key, and encrypt that data and return it using AES 256 GCM and return that back to the calling application to the customer. And last year, we walked through this specific small portion of this that we called the KMS derived key mode for GCM. We presented that in detail here, so you can see that presentation last year from Shai Goran, where when you look at AWS, the KMS service as a whole, and you look at how it's encrypting, that across all the customer master keys and all the sort of derived key encryptions, that the system can support up to 240 master keys, all doing 250 encryptions, while ensuring that the probability of a key IV collision and an adversary's pseudorandom permutation, pseudorandom function distinguishability advantage stays below 1/232. This is a little bit looking through a rear view mirror. This was designed in 2013, and while we did have a FIPS requirement, and there's certainly other methods that we could have used, the modern method of like SIV was just not known to us at the time. And this is the solution that we developed internally and deployed for this system. From a more macro perspective, the service is a little more complicated. And in particular, we build AWS's cloud is sort of built in geographical regions that we refer to as regions, and they consist of multiple availability zones. So today we have 20 regions worldwide with 60 different availability zones, which are designed to be sort of our fault barrier for services. So the service is designed so that any of the state management sort of happens at the control plane level. So things like creation of keys, putting a key policy, enabling a key or disabling a key, all require sort of a state transition through the KMS service. And it's optimized so that the data plane operations don't require state transition. And this sort of desire not to have to distribute state or be able to handle simultaneous calls to encrypt sort of forces your hand not to use like a counter-base IV, which would be a logical way to extend the usage of a key using GCM. And again, the system is designed to handle failovers. So the HSMs go down, the availability zones will communicate with each other, and the service continues to run with the loss of availability zones. So today, KMS is integrated into 48 different services, and we're continuing to integrate that into new services as it makes sense that there's value in protecting the customer data that's transferring through those services. But there are certainly natural limits on a centralized service like this, and to avoid sort of, I'll say, design patterns where people are shipping all their data through KMS, there's a limit on the amount of data that you can encrypt in KMS, and that's 496 bytes. So that immediately comes up with, when we're doing all these integrations, different patterns kind of pop out. And one clear pattern that pops out is envelope encryption. So when we think about envelope encryption, it's sort of a natural integration pattern where a customer would call the generate data key and against their master key and get back both the encrypted data key and the data key itself. And then they can use that to encrypt their plain text, throw away the data key, and store the encrypted data, the pair of the encrypted data key and the ciphertext value. And that solves a large number of the use cases that both our customers see and our integration patterns internally. But it doesn't solve all. And in particular, customers and applications have policies that look like this. So this is sort of it looks like it could be two clauses on a key policy. The first clause basically says that Alice can generate a data key or encrypt, and it says Bob and Charlie can decrypt. So it looks pretty innocuous, but what happens here is the policy on the raw encrypt expressed in the key policy doesn't extend over the envelope encrypted portion of this data, meaning that Bob can legitimately call decrypt, get the data key, create a second message, and send it off to Charlie, and Charlie has no way to detect that this didn't come from Alice. So putting all these sort of integration patterns, edge cases, selection of algorithms and IV generation into the hands of our customers, just sets them up for having to spend a lot of extra time and effort to engineer these solutions. And they're ones that we've sort of seen in the wild, either through speaking with our customers or doing these integration patterns that sort of set the requirements for us developing the AWS encryption SDK. And its fundamental goal is to sort of make it easy by default. Like if you just use it, it does the right thing. It thinks around these edge cases. It handles envelope encryption for you, so you can encrypt large data sets. And it extends the policy from the master key over the envelope encrypted data. And finally, it allows you to scale your calls to KMS. So like many cloud services, it takes an outbound call to get a data key. And that's going to add latency to high frequency encryption. There has a caching layer built in that will decrease that latency as well as decrease cost of using KMS. So the structure of the encryption SDK for doing client-side encryption. So the lower right box is the encryption SDK that's processing a plain text. And the first thing it'll do is sort of generate an ephemeral signing key and then make a call to KMS to generate a data key. And in that call, it'll bind that public key to the encryption of the data key by adding the associated public key into the additionally authenticated data that's encrypted, used in the encryption of the data key. And it can start building the ciphertext structure. It generates a fresh message ID, derives a new encryption key for that message ID, and as the parts of this plain text comes in, let's say it's a streaming application, it will use a counter-based IV, AES GCM, encrypt that, and put the parts together, and just add the parts to either the stream or the structure of this ciphertext. It'll process all those parts, and then add on a digital signature at the end. And now, a recipient of this, like Bob, can no longer change the message without either being able to call generate data key or encrypt, binding a new public key to the encryption context or the AAD, or learning the signing key D. And then Alice can reuse this data key and signing key on subsequent messages. So on the next message that comes in, she generates a new message ID, derives a second encryption key, and encrypts all the parts and sends it on its way. So here, of course, is some of the, you have to think about, are we going to run into key IV collisions? I should say this is sort of the default method that's being used by the SDK, and it uses 256-bit keys. And so when you look at the probability of a key IV collision, it really just comes down to, because we're using a counter-based deterministic IV on the parts, just comes down to the key collision. And the analysis on that, if you look at just, let's say you're doing n many cache keys, each of which is doing q many derivations, the probability of a collision, if you look at that just as random, is fairly negligible. When n and q are less than 2 to the 32, this is less than 1 over 2 to the 129. But within a particular data key, because the message ID is relatively small, that probability of a collision for one derived key for a fixed data key is roughly 1 over 2 to the 60, well, it's less than 1 over 2 to the 64 as long as the number of encryptions are less than 2 to the 32. So in general, if you're doing n many cache keys, you still maintain, if you're doing 2 to the 32 many cache keys, each of which doing less than 2 to the 32 derivations, you still retain the probability of being less than 1 over 2 to the 32. So you're really in this single user, multi-cache key, multi-key encryption scenario, but the fact that they're large keys and deterministic IVs make the probabilities of so-called bad events sufficiently small for the customer. So the encryption SDK, like I said, by default, uses AES 256 GCM, uses ECDSA on SecP 384R1, and it's an open source solution, and on the last page I have some links to downloading the various versions of this, or supported language for this. But it supports message sizes up to 2 to the 63 bytes. You can use it for framing of data for streaming. It'll support caching of the data key, under sort of a security context or an encryption context that you're doing encryption, and then you can configure it based on time, the number of derived keys or bytes. And by default and by design, it doesn't allow you to exceed 2 to the 32 derived keys. And finally, the fact that it was designed to be extensible to additional key management infrastructures, and there's practically what I would call a developer's developer kit for how to extend this to additional KMIs. So where you might use the encryption SDK are in distributed applications like Kinesis. So Amazon Kinesis data streams allow you to collect and process large streams of data records in real time. And you'd have a set of producing applications that might be taking readings from your network. Let's say it's a sensor network, and you want end-to-end encryption. You can use the AWS encryption SDK to sort of, if you're taking 1,000 readings a second, you don't want to be making 1,000 API calls to KMS for every encryption. So you can cache that data key and leverage the calls across. And similarly, on the consumer side, reading in from the data stream, you can leverage the number of calls that you're making, reducing not just the latency of your applications, but your overall cost of running those applications. So that brings us back to encrypting objects in S3. Of course, we're using TLS, making TLS available to upload all your objects to S3. But you can use AWS encryption SDK to do client-side encryption, or additionally, there's the S3 encryption client that's built into our standard AWS SDK. But you can also configure it to do server-side encryption, which is an easier way. You can just sort of say, when you put the object, specify the KMS key ID and encrypt it while at rest. So when you put an object into S3 with server-side encryption, the first thing that happens is a call is made on behalf of the customer, provided that the master key allows you to encrypt under it. It'll generate a data key and get an encrypted data key and that data key and store the encrypted data key in the object metadata. It'll then break up that object into chunks. And for each one of these chunks, it will encrypt it using AES GCM and storing the IV and tag along with the chunk. So this adds, of course, 12 bytes of IV and 16 bytes of MAC per chunk. And we're using a random IV here. It's not clear in this picture why that's needed. But in the parallel upload process, when you're uploading the parts in parallel, again, you're left with this problem of managing the state or distributing the state of your counter across all your upload nodes. And the reason that we're doing encrypting sort of in chunks is predicated on the existing APIs that allow you to do so-called range gets. So when you try to get an object, if it's a 5 terabyte object and you only need 20 bytes of it, you're not going to want to download the 5 terabytes and then seek through it to get the necessary bytes. You can rely on the APIs to do that for you. So when you call getObject, the service will make a call back to KMS on your behalf with the encrypted data keys stored in the metadata, get the necessary chunks, process those chunks, and then reassemble the range and return them back to you. Of course, that leaves you with a couple of design decisions in terms of how big are you going to make these chunks in practice. So with a 5 terabyte limit, you have some flexibility on how big 5 terabytes is the current limit for an object within S3. You have some options on how big these chunks are. But if you make the chunk, let's say, small, you're going to effects of that is you're going to increase your overall storage overhead. and you're going to lower the amount of data that you can encrypt under a single key, because you can still only do 2 to the 32 chunks before you sort of reach a bad probability. So that limits the total like to 8 terabytes. Of course, you can go with a larger chunk size that has the property that's certainly going to reduce your overhead and increase the maximum amount of data you can store, but now you're increasing the latency on these range gets, which are fairly common in how people are using S3. All right, so in summary, I think, following up on sort of Professor Masurik from yesterday from University of Maryland, I think AWS is really trying to make encryption of customer data easy with secure default configurations. So customers don't have to do the IV generation. Think about the difference between confidentiality and authentication. What customers really want is to have their data secure, know that it's secured using algorithms that are well established and standardized and meet their requirements and their auditors' requirements. That there's general tension between the one-size-fits-all and every application requires a custom solution. When you're doing just 48 server-side integrations, you're really trying to minimize the design patterns and the tools to implement those patterns so that you can make them higher assurance, be more robust, and easier to reason about long-term as you're monitoring what's going on in the state of the art. How many tools do you have to now go and update because there have been changes? And I think, in general, probably not unique to cloud providers, but managing state across distributed systems is really performance inhibiting when you're looking at being on the encrypt-decrypt path. And that really comes out when you're looking at IV collisions, and you can't distribute sort of a counter across parallel systems to operate. And you can't really rely on breaking up that counter long-term over the lifetime of the service. So, a lot of this work becomes a lot more simple if I had an efficient, standardized, and wide block encryption algorithm that would certainly simplify a lot of these tensions where we're really going out of our way to sort of stretch the IVs because we have a 128-bit block cipher. So this is my last slide. I have links to additional details for both the KMS service, client-side and server-side encryption for S3, as well as the open source links to the encryption SDK, where you can also find the format in additional detail. Thank you. Thanks.
We have time for questions. So there are 3 microphones in the room. If you want to make any questions or comments to Matt, please show up. And here we have the first question.
Very nice talk. So can you say a little bit more about what other algorithms you looked at? Is it a standardization issue in terms of using something besides ASGCM, or is it a performance thing?
So in the toolkit itself, the encryption SDK, you certainly can specify additional algorithms and implement, because it's open source, you can implement your own in there pretty freely. Within the KMS service, we certainly did labor over, should we use a key wrap, which left, a big part of the efficiency of that data plane was making sure, going over that data path once using AES-GCM was very attractive. We did look at CTR, like HMAC combination, but ultimately GCM was the one that we saw was going to be giving us the highest throughput.
Yeah, thanks for the talk. I'm curious, could you talk a little bit about how fault tolerance works? So how you recover, say, from the failure of an HSM and these types of things?
Yeah, so kind of hidden in there is, with the domain key, this notion of a domain within a KMS region. that consists of sort of credentials for all the HSMs as well as the KMS servers that need to talk to them. And there is a state management across those HSMs. But that doesn't occur either in the control plane of the customer creating and changing keys or the data plane of encrypting and decrypting. So that the back-end service is managed through another service to sort of maintain state, consistent state across the HSMs.
Any other questions, comments? Okay, let's thank the speaker again.
Great, thanks.
Okay, you ready?
Yeah, one second.
So the next speaker is Siva from Visa Research, and he'll be talking to us about applying proxy re-encryption to payments. Okay.
Sorry for that. Today we talk about few problems in payments domain where proxy encryption help address them effectively. This is a joint effort between my colleagues Atul and Rohit. That's our employer's disclaimer. It's basically trust but verify offline. It all starts when consumer wants to pay a merchant digitally. Today, consumer needs to have a relation with consumer bank, gets his card, and similarly, merchant needs to have a relation with merchant bank. And all these two entities are connected with payment network, and merchant gets his point of sale terminal from the merchant bank. Moreover, the merchant would talk to the merchant bank via these two additional players called point of sale partner and the payment gateway. The reason why these two players exist because, let's say, for example, if you're really a big merchant and you want to go globally, and you need a point of sale partner because you want to manage this heterogeneous point of sale hardware. In case of payment gateway, it basically helps you work with local merchant banks. Let's see how the transaction flow works at very high level and see what each and every actor does. Let's say when the consumer swipes a card, the point of sale partner receives the transaction first and then sends it to the payment gateway. And the payment gateway simply forward to the right merchant bank. And then merchant bank would simply forward to the payment network. And payment network does these three functions and then further send it to the consumer bank for authorization. Today we are going to focus on these three functions. As we've seen previously, the payment network receives the transaction from merchant bank and basically does three functions sequentially, where basically map is some kind of a stateful operation and then gives it to the auth. Auth basically performs some kind of a cryptographic operation and then gives it to the route, and route basically transforms the message in such a way that consumer bank can understand it. As we see here, the main the operation here, auth box, basically performs a lot of cryptographic operations, which involve CV verification, chip verification, etc., etc. Let's see a few sample what we do on a daily basis. Let's say when you swipe a credit card at point of sale, the auth box or auth function receives the PAN data and the CV as an input, and then some kind of keys as an input too, and then outputs 1 or 0. Whereas in the chip-based transaction, the point of sale gets the cryptogram from the chip and then pass it on to this auth function. It also uses some additional new keys to verify this cryptogram and then outputs 1 or 0. Whereas in the case of debit transaction, the PIN has to be verified securely. Today, the PIN can be verified either by the consumer bank or the payment network and uses the same function. As we see here, every transaction involves some type of cryptographic operation. And we do at large scale, like for example, Visa reported last quarter, like Q4, we processed like 5,000 messages per second approximately, and then which includes 2,000 debit and credit. Since each and every transaction involves some kind of cryptography, all the entities in the network has to use HSM to protect the sensitive key material securely. Today we are focused on see if at least one type of transaction we can reduce the HSM burden on the entire ecosystem, not just one player. As we've seen previously, auth function takes transaction input and outputs 1 or 0 by using a bunch of HSM machines. As we've seen previously, the top hitters are credit and debit, which translates to the CV verification, ARQC verification, and the PIN verification. These are the top 3 headers in the sequential manner. So we're going to focus on the PIN verification today because we believe basically we can actually help reduce HSM burden on this type of transaction. Today there are 2 PIN verification modes exist. PIN can be verified online. What it means is that PIN has to be sent securely to the consumer bank. Whereas in case of offline, card can basically verify it. Obviously, it seems risky, right? Because most of the consumer banks don't want to do this. They would like to verify the transaction online. Today's the rest of the talk focus on online PIN verification. Okay, let's look at the simple debit transaction. Okay, in order to do the debit transaction, at least the chip card should have at least these 3 pieces of data: a track data and a simple counter and some unique secret key. Let's say, for example, this counter is 16-bit. You end up having 3 years of validity. Track data would have a PAN data. And there is this one flag which says that this card supports online PIN verification. Now at the time of payment, PAS would basically send terminal data, which has some random nonce, to the chip card. And chip card basically does these 2 sequentially. It generates some session key, and then generates a cryptogram out of the point of sale data and some using that key, and then send it to the point of sale terminal. Now the PAS will ask the consumer to enter the PIN since the flag says to do so. Okay, now the problem is that the PAS has to send this PIN securely to the consumer bank for authorization via these many players in the network. Okay, what PAS does is at the moment it receives the PIN immediately, it encrypts the PIN using the key fused on the hardware or get the key from the payment gateway, and let's call it as encrypted PIN block, and then send it to the other players, and finally reaches the consumer bank. And all other players in the network invoke a function called PIN translation, which involves HSM, to achieve PIN confidentiality. So let's define what is PIN translation means. PIN translation basically takes ciphertext and input and outputs another ciphertext, and it does a triple dash decrypt and encrypt in middle. Okay, in order to do this, today what we do is that we basically share keys, okay, a priori. So let's say, for example, merchant bank and consumer bank use payment network as a key custodian, and merchant bank and point of sale partners you would use payment gateway as a key custodian. And first, at step 1, payment network would generate 2 unique keys and then give it to the merchant bank and consumer bank. And similarly, merchant bank would generate a fresh key and give it to the payment gateway. Whenever the point of sale partner comes to the payment gateway, you would generate another key and give it to the point of sale partners. Using this setup, today we achieve because of this, now payment network end up storing the keys equivalent to number of merchant banks plus number of consumer banks. In case of payment gateway, we end up storing number of point of sale partners plus number of merchant bank keys. To achieve PIN confidentiality, PAS would send the PIN to the partner, and then partner would generate the encrypted PIN block and send it to the payment gateway, and then payment gateway decrypts it, encrypts against the merchant bank's key. Merchant bank does the same thing against the payment network key. Payment network does the same thing against the consumer bank key. Now finally consumer bank can decrypt it and then authorize the transaction further. Okay, what is the problem with this setup, right? So let's look into the problems. So what happens is that since it's a symmetric key, since the setup is a symmetric key in nature, the payment network would have to refresh the keys more often, and these key changes would have to further sent across the downstream. The problem is that, for example, if for some reason if the key refresh did not go as expected, now the key custodians would end up having the problem whether to decline or whether to accept by using some kind of workarounds. Okay? And moreover, these HFMs are hard to scale. And it also increases the burden on all the players in the ecosystem. Let's say, for example, how do we solve these problems, right? Obviously, obviously we would go for the public key schemes, whether see if they solve the problem. Let's say if there is a scheme exists, okay, and if it solves a problem, what are the requirements we should meet? So requirements are of the following. It should support all types of payment types, okay, and it should also reduce some burden on HSMs. And also, it should incur minimal changes ecosystem for successful deployment. These are the main 3 requirements. Okay, the main question is that, can we use traditional PKI or available traditional PKI to solve the problem? Okay, given this setting, let's say let's get ambitious, and then consumer bank generates a key pair and then send all the keys to the point of sale terminal. But the problem is that most of the point of sales do not have enough space to do this. Okay, the other option is basically share these keys with these 2 parties. But the problem is that they don't know which key to use. They end up needing a map table from the payment network. So either a payment network would have to share this map table to these players, or they would have to, the payment network would have to implement this online service, or they would have to change the entire transaction flow. Other option is basically share the network keys to the POS terminal directly, but the problem here is that the payment network still need an HSM, and moreover, merchant may lose the flexibility in routing. Okay, if you really want to go this route, let's do more smarter approach. Let's use the chip card basically. So anyway, chip card comes from the consumer bank. So what can we do is that let's the consumer bank burn the keys as part of the chip card. Okay, unfortunately there is a setting called offline data authentication in the current EME spec. So what it basically means is that when you basically insert the chip card in the POS terminal, POS basically verifies whether this card is coming from the right entity or not. We could use that flow to solve this problem. In order to do this, basically the consumer bank burn these extra keys, which is basically the bank's public key and the certificate. So, and then at the time of payment, basically the POS verifies the card whether it's coming from the right entity or not. But the problem is that, as we've seen before, our requirement is to support all types of payment types. Obviously, the max stripe would not have this extra material, and you end up breaking the entire ecosystem if you go this route. And moreover, ODA is optional and increases the cost on the consumer bank. Since it's an optional and increases the cost, you end up having, even though you have a chip cards, they may not have this setup at all available. Okay, what can we do about it? So when we looked at the scheme, we find the proxy re-encryption interesting, and it solves the problem effectively. And I will explain you why it solves a problem and what scheme we use it and why we use it. See, just in case if you don't know what PRE means, similar to the PKE, public key crypto, you get these additional 2 methods called re-keys and re-encryption keys. The traditional use case, what's outlined in the research papers is that, let's say if Alice wants to send a lot of data, Alice wants to send encrypted data to a lot of parties, either Alice would have to encrypt data against all the public keys or share the secret keys, or instead she can basically delegate the responsibility to some proxy to basically translate the ciphertext to someone else's ciphertext based on their public keys. So the way it works is that Alice needs a proxy. Obviously, it gets the public key of the Bob from the proxy and then gives the re-encryption keys and then gives the encrypted message and goes offline. Bob can come later and basically request for the re-encrypted ciphertext and can basically decrypt after that. So we need to understand properties before we move on to the next slide. So most of in general, PRE schemes comes over these properties. Let's say unidirectional or bidirectional. What does it mean is that proxy can, in case of unidirectional, proxy can only translate ciphertext from Alice to Bob, whereas in case of bidirectional, proxy can translate from both ways. What collision safe means is, let's say proxy and Bob can collude. They should not be able to learn the Alice's secret key. Non-interactive means, let's say, for example, Alice and Bob should not want to be online at the time of generating these re-encryption keys, which is a desired property, right? When it comes to the and it also have a non-transitive properties. What it means is that let's expand the setting a little more. Let's say you have A has a relation with B via proxy 1, and B has a relation with C with the proxy 2. Let's say, for example, proxy 1 and proxy 2 is able to translate ciphertext from A to B via re-encryption keys. Using these keys, proxy 1 and proxy 2 would not be able to divert the ciphertext to Charlie without A's consent, with Alice's consent, okay, which is also desired property. Okay, now using the setting, Okay, let's see how at high level, how the pin translation works. Okay, we all replace this traditional pin translation boxes by invoking these functions. Point of sale partner would invoke a pre.enc function. Payment gateway and the payment network simply do a re-encryption, and merchant bank does no work at all. It simply forwards it, and consumer bank does one extra decryption operation and then basically authorizes the transaction. Okay, which scheme we should use? Okay, so the main important properties what you want from a PRE scheme is that it should be transitive, not non-transitive. It should be transitive because we don't want the merchant bank to do any extra work, and non-interactive. So that means nobody should not know each other's secret key. Okay, if you look at the literature, apparently it's kind of hard to get these two properties together. Fortunately, we were able to fit BBS scheme to address our setting. Unfortunately, the BBS scheme is not non-interactive; it's more of an interactive. Because of our trust model, we can actually relax this requirement. And moreover, BBS has one more problem. Let's say, for example, if proxy and recipient can collude, then source can basically get the secret key of the if the proxy and recipient can collude, then they would be able to learn the source's secret key. Because of our trust model, we can also get around with that. Let's look into the key setup using this scheme. Obviously, we have these many players. We need to see payment network and merchant bank needs to be trusted. The reason is that merchant bank does a lot of work on certifying the point of sale terminals. But why do we need to choose payment network as a trusted party? Let's say, for example, during the online phase, consumer bank can go offline. Okay, for them, going offline means they have a problem, right? What should we do when their customer is basically making a payment, right? If the consumer bank goes offline, now the option for the payment network to decline a transaction. So declining a transaction is not an acceptable criteria. In that case, what they do is that they would end up sharing the secret keys with the payment network anyway. Because of the trust model, what can we do in this scheme is that payment network can generate these keys for both of these parties, and then also share these keys in secure to the both consumer bank and merchant bank, and payment network can keep the re-encryption keys to itself. Okay. Now, since the merchant bank is a trusted party, now what it does is it generates the keys for the point of sale partner and generate the re-encryption keys for the payment gateway, and then only share the public key to the point of sale partner. Okay, and shares the re-encryption keys to the payment gateway. Now, in this case, even though payment gateway and point of sale partner can collude, they would not be able to learn the merchant bank secret key. So we can keep the leftmost parties remain say untrusted. All the rightmost can stay trusted. As you see here, we have two entities which are trusted and untrusted. Now we end up storing more keys. Let's say, for example, payment network storing the keys equivalent to number of merchant banks times number of consumer banks. But the payment gateway, you would have storing number of point of sale partners times number of merchant banks. Let's see how the transaction flow works in case of a new setting. Now, when the point of sale receives the PIN, it uses simply its public key to encrypt the PIN, and then sends the encrypted PIN block to payment gateway. Now, the payment gateway uses a re-encrypt operation to translate to the merchant bank. Merchant bank simply does forward. Payment network does one more re-encrypt and give it to the consumer bank. Consumer bank does one extra decrypt operation and then perform the authorization. As we clearly see, the advantage here is that now the payment network and payment gateway no longer need to use HSM for this particular type of transaction. And moreover, merchant bank does nothing. He just simple forward. Whereas in case of payment network, they don't have to worry about key refresh at all, thereby processing transactions more efficiently. And we got this weakness of BBS scheme around in our, we got this workaround of the weakness of BBS scheme in our trust model by making these two parties collusion safe. Okay, so I'm presenting some experimental benchmarks here. So the main important metric we care about is end-to-end latency. Because of the scheme, we are going to add extra overhead on each and every parties. Let's say, for example, point of sale partner would end up spending close to a millisecond, and rest of the parties spend less than a millisecond. But if you look at the overall end-to-end latency, which is insignificant compared to the total transaction time you spend when it comes to the total payment. Okay, so throughput is easy to achieve. We just need at least greater than 10K. for the pin translation, which means basically the bunch of re-encrypt operations, which is easy to scale just by using 4 nodes. When it comes to the space overhead, as you see here, payment network went from number of merchant banks plus number of consumer bank keys to number of merchant banks times number of consumer banks. It looks asymptotically bad, but in practice, it's negligible. I mean, we can actually fit into the commodity RAM. As we see here, the PRE-based pin confidentiality supports all the post requirements, which basically supports all types of payment types, includes the legacy, and also reduces HSM reliance on and the entire ecosystem for this particular payment type. Okay, so now the biggest problem is that we claim that we are going to incur minimal changes, right? We cannot deploy this scheme without adding one extra field to the message set what we have. Obviously, it may be expensive to deploy it right away as part of the global payment, but at least the local domestic card processing networks would see the immediate advantage of this scheme, because basically most of the payment networks are global in nature, whereas in case of domestic card processing networks will only deal with in-country specific traffic. There you would not see a big deal to implement to basically take it to the next level. Today I'm going to talk about another problem at very high level. Today merchants loses a lot of money because of the cart abandonments. In general, consumers abandon the carts due to 3 reasons. Mainly can be classified into 2 categories. The first and 2 are basically the security, because consumers don't trust these merchants with their credentials. And the third one is much more interesting because they don't find a lot of payment options available in that merchant website, which is a very difficult problem, right? The reason why it doesn't exist because it's an unknown payment type. When I say unknown payment type, a payment type which is popular in consumer doesn't mean a merchant should accept it, doesn't mean it's widely acceptable, right? A payment system which is not widely acceptable is not a payment system at all. Okay, but still some consumers wants to use a payment system to pay, right? How do we support these kind of edge cases or corner cases? If you dig deeper in this question, we're gonna get one interesting requirement, right? How do we help merchants process unknown payment types, right? Here, let's say for example, the way we solve this problem is that, let's say for example, we need to turn these payment credentials into some kind of a cipher text, and basically help merchants take the ciphertext and process payments based on that. Because of the ciphertext, we can actually help consumers to proliferate the ciphertext to all the apps he would like to use, okay, without compromising the confidentiality. Now the problem is that the payment gateway is a simple abstraction of, it takes the input of PAN data, plain PAN data, and then outputs 1 or 0, right? But how do we help payment gateway process this ciphertext, right? We need to introduce the CT provider, which is the one who provides the ciphertext in the first place, so that payment gateway can invoke this particular entity to get the actual plain data and then process a payment. But the problem is that you can't expect the providers to be online all the time, okay? So because of the PRE, they can initiate once, give it to the consumer, and they can go offline, and they can delegate the responsibility to one entity here. Okay. Now, but that one entity not only trusted, now that new entity is trusted for even enforcing the policies of re-encryptions against unknown parties as well. So in that case, we kind of envision a scheme where we combine these 3 primitives for which involves proxy re-encryption, IntelliJ and blockchain to address that problem. Which is basically like a system which sits in between 2 worlds, which is untrusted world and untrusted world, like Sakar in the Avengers movie. Okay, thank you. As we see here, we showed the PRE scheme helps address the pin confidentiality without using HSMs at all in the entire ecosystem. When it comes to e-commerce, PRE can help consumers choose any preferred mobile application for checkout. Thank you.
We have time for questions. Do you want to use the microphone over there? That's the closest.
Yeah, just a quick question. The proxy re-encryption scheme you used, BBS 98, is only CPA secure.
Exactly.
Does it create any problems for your solution, or it's
so what we
enough?
do in this case is that we are going to use it for we are going to use it as a hybrid encryption. So the point of sale party is going to generate the fresh key every time, and then encrypts a pin using that, and then we only wrap that key every time using PRE.
Mm-hmm.
I have a question. What is the state of this implementation? Is it proof of concept? Do you have any plans to implement it? And if you do, when?
This requires a standardization effort. We are working with the local domestic card processing teams to do that.
Do they have any plans or dates when this is going to be implemented?
We are working with the standardization right now.
Oh, you don't? Okay, thank you.
Hi. Earlier you showed a slide on the latency of the new system, and I was just wondering how that compared to the HSM-based solution.
Okay. Because in the previous, today what we use is we use a lot of symmetric keys and use HSMs to do the pin translation. Basically, HSM receives an input, and then inside it does a decrypt using triple des, and then encrypts. Again, it's the recipient secret key. In the PRE, you don't have to use HSM at all. Since our re-encryption key is a public key, you can do it in memory. You don't need HSM for that.
Okay, so is this faster than before then?
No, it would be slow, but it would be secure. But the desired scale, we can actually achieve it even in the new scheme too.
Okay, thanks.
Hi. Did you say that since you use BBS 98, then it's safe to assume that your current scheme is currently interactive?
No, it's here. What we do is that we get around that requirement by let the payment network does the key ceremony.
So so the payment network itself, like for BBS 98, it's done by Alice's private key being divided by Bob's private key. So so the payment network computes this itself and then distributes the re-encryption key?
Yeah, exactly. The reason they do it is because right now the consumer bank can go offline. In that case, they would have to share the secret keys anyway to the payment network. Here, when it comes to the processing transaction, for them the biggest goal is to process the payment, right? So for that, that's the main priority. So they would end up sharing the key with the payment network anyway.
Okay, thank you.
Hello. A question here. So using HSM scheme, you were using triple des there in the HSM. Now in the new scheme without HSM, are we still continuing with triple des, or now we are using AES with AAD? And
so like I said, so we are going to use hybrid encryption. We are going to wrap the symmetric using PRE. Okay. So all the entities in the ecosystem, they do the public key operations. No longer require a symmetric operation, thereby eliminating the need for HSMs. In the online phase, payment networks still have to use HSM. Because it has to authorize the PIN.
Thank you, and great talk. Thanks.
Yeah, just one more question. So what you do with proxy re-encryption falls to transformational encryption category, right? And I've seen some skepticism in academical and industry about strengths of transformational encryption in general. So probably it's the same, no problem with homomorphic encryption. So did you do any serious research with a third party to make sure that this concern is resolved?
Okay, so I'm not sure about any other schemes which helps us solve this problem, but I'm happy to know offline.
Okay, thank you.
Back to the first question, that once was not clear for me, because even if we use hybrid encryption, if proxy encryption is CPA secure, then I don't think it's safe against the CC attack.
Like I mentioned previously, so what we do is that we don't...
BSS scheme is not CCA secure.
That is absolutely true. So what we do in this case is that we let the point of sale partner generate the fresh key every time, and then prepares the EPB encrypted pin block using that key, and then use a PRE to encrypt the key, freshly generated key.
Okay, so let's talk offline. Yeah.
Okay, I can explain offline. Yeah.
Okay, you might have already covered this with some of your previous answers, but the BBS scheme, why did you go for the BBS 98 scheme as opposed to a more recent scheme where to generate the update token you need Bob's public key instead of his private one?
Can you say that again? I'm sorry.
Why didn't you consider any of the more recent proxy re-encryption schemes where you don't need both secret keys to generate the update token?
Why I don't need what?
Well, in the BBS 98 scheme, you need Alice's secret key and Bob's secret key to create the update token. But there are more recent schemes where you'd only need Bob's public key. So why using BBS 98?
So the biggest problem here is that we need a transitive property in it. So if any scheme which is non-interactive and a transitive, which has a transitive property, that may be interesting.
Right. Okay.
Okay. But most of the schemes I looked at, like for example AFGH or some other schemes, they don't have a transitive property available. If I don't have a transitive property, then merchant bank has to do extra work, which they end up not deploying the solution at all.
Okay. Thanks.
Okay, no more questions. Let's thank the speaker again. Thank you.
Thank you.
The microphone? Okay, the last talk of this session is by Max from Keybase, and he'll be talking to us about managing teams and keys with Keybase.io. Oh, okay.
Thanks. Can you guys hear okay? Microphone on? Okay, good. So in preparing this talk, I took a couple minutes to sit down and write out the apps I use the most on my phone and on my desktop. And I came up with this list. There's email on there, there's a phone app, there's Slack, there's SMS, GitHub, Dropbox. That's Confluence, it's a wiki product, and also something like Google Docs. And we've heard a lot about the green ones, so let's ignore them for now. I want to talk about everything else. I think if we reflect upon where we are right now, in a lot of ways, we're almost worse off than we were like 10 years ago, because right now we're uploading all of our unencrypted data to like these centralized honeypots. And at least before, we used to manage those honeypots ourselves. So this is me as a grad student about 15 years ago, and I had a lot of cool stuff going on my server. You see I got a great CRT there, but I ran my own mail server, my own CVS server, my own wiki. If you needed a file, just SCP it from my machine. So in some ways, we were better off then. A lot of great things going on at 18.26.4.239. And as a sign of the times, MIT actually sold that IP address to AWS. So literally. And so this is where we are today. We can look back at this period with nostalgia, but it turns out that federated management, though better than what we have, was never really good enough. And I was talking to a head of security at a really big mega software corporation. And their conundrum is as follows. If they want to run Slack internally, that's bad because all their secrets are now just running out of the company as fast as people can type. And even something like, let's say you run like a HipChat server internally, that's almost just as bad because now the SREs have access to all the private data going back and forth. So that's not really going to cut it. And so, maybe we can say that, this ship has sailed, that managed apps in the cloud is kind of the future. And because we're here and not at some other conference arguing about block sizes and 51% attacks, I think we all might be on board with that assertion that, managed apps in the cloud might be the way things are going. But, at the very least, can we please get decentralized trust and key management? And that's something that we should all answer, resoundingly yes to. So that's what I'm going to talk about today. And even though I feel like I could talk about those other apps, I'm going to focus on something like Slack. How do we build an end-to-end secure Slack? So the first thing we might want to talk about are, what are the basic requirements? And I think number one has to be multi-device support. And it's not like, it's like really good multi-device support. And what I mean by that is like imagine somebody buys you a new phone for Christmas. what you really expect in a Slack-like experience is to enter your username and password and to get instant access to all the history you've ever had in that Slack channel, right? That's what people expect. So that's what I mean by multi-device support. And moreover, in addition, you might want things like nameable teams with mutable membership. And if anyone's ever worked out in the real world, obviously people get fired, people get hired. That type of thing is a pretty common occurrence. So whatever we build, it really ought to accommodate that situation. And finally, I don't know if anyone's recently invited someone into a Slack team recently, but the way that's done is with email, right? And so that's obviously very centrally managed, centrally authenticated. And if you're going to have an end-to-end secure Slack where you're inviting new people in, can you come up with a better authentication system that isn't this roughly centralized, trusted email authentication? And what threat model should we consider? I suggest we should consider the real one, which is that the bad guys own the server infrastructure. And we know this is, so in other words, not just like passive adversaries, but adversaries who get into the whatever server-side stuff is running and can do whatever they want. And just last month there was a big news article. GCHQ is considering a proposal. We saw this. We're like, we've been saying this since 2013. This is the problem. It's not just the barista at Starbucks. It's that anything you run on a server, there's no reason for anyone to trust it. And given those requirements and that attack model, what are the security goals? So in this talk, I'm going to talk about offering post-compromise security by default. And I know forward secrecy is a hot topic. In our key-based product, it's opt-in. So you don't, and a lot of use cases, you might not want forward secrecy. Imagine just your Slack channel where you're talking about all your development or some sort of technical details. You probably want that to persist and be indexable and searchable to even people who are just joining the team. So it could be that forward secrecy might make sense when you're talking about salary negotiations, but maybe for other things, it doesn't really make sense. So I'm not going to really touch it much in this talk, but it's you can layer it on top of what I'm going to present. All right, let's spend a couple of seconds talking about insufficient solutions. If you're an old PGP user, you probably have this kind of model in your mind, which is that you just put your master key on a USB drive. You just walk on down to your bank and you put that USB key in the vault and kind of use it every 2 years when you roll your subkeys. That's not probably practical for a lot of people. Something that's actually catching on, which is a great thing in a lot of ways, is a YubiKey. And so this is actually my keychain. And notice I've redacted it so you guys don't let yourself into my apartment. And I know this audience. So the YubiKey is, in a way, is a lot better than the previous slide or other alternatives. But raise your hand if you've never lost your keys. Oh, couple hands. Okay. So not a great solution. And I could be wrong, but I think this is the Signal story now, where you have like one master device, and that's actually powering your other devices. That's like another solution. I think it's better than the YubiKey example because you could put some layers of security on top of the key, which is harder to do with the YubiKey. But even then, you could still lose your phone, and so that's also not a great solution as far as we're concerned. Okay, so Keybase's approach is as follows. So users need to start thinking a little bit about keys, but not in the way that will make their eyes glaze over. So we say, users, you think about devices, and there's more or less like a one-to-one mapping between a device and a key. And so in that model, so each user can have multiple devices, and I have 10, and you probably have something around that number when you consider your work computer, your laptop, your desktop, your phones. And in our model, we're going to say that each of these devices is equally powerful. And I think there's a lot of good aspects of this proposal. First, we've obviously all lost phones, individual devices. They're very easy to lose. But with this equally powerful model, now the more devices you have, the less likely you are to lose your data. And if you need a real key to decrypt your data, totally do not want to lose your data. That's like priority number one. It's even like more important than like encryption. It's just like people hate losing their data. And also, I'll mention that you're most likely to discard your oldest device, right? that's like the one you bought the longest time ago. That's the worst of your devices. And so we don't want to build some system where like you're required to keep your like first device. That would obviously not be practical. So we're going to build up an abstraction that's actually reusable in the team setting. So if we're going to say that a user is a collection of devices, and similarly, a team is a collection of users. So this is almost like a concept that we could use twice in the building of the system. And if you stitch these ideas together, I'm claiming that you wind up with a very usable interface that people can actually understand. And just as a little preview, this is what it looks like right now on our live app. On the left, to manage your devices, and so this is a list of all my devices, including if I click on that button, you can see my revoked devices, which I've certainly done in the past. And managing users is almost just as simple. You have a nice user-friendly kind of display of what a team looks like. So how should we make apps work on this model? It's a pretty simple story. So every team in Keybase we're going to build up to is going to have a random shared symmetric key. And it's going to rotate whenever users are removed from the team or whenever anyone on the team revokes a device. And so when users actually write into a chat channel or a Git repository or a file system, really those updates are going to be encrypted for the current shared team symmetric key and then signed by the device that made the update. And this last thing is just to prevent Alice and Bob from kind of putting words into each other's mouth, from misattributing updates. With those very simple primitives, you can kind of build more or less a full-featured app. So this is a Slack application. It has unfurling, it has React.js, it has channels, it has multiple teams. All this stuff is possible with just those very simple crypto primitives. So I think what's left to drill down a little bit deeper is my initial claims. How do devices come together to sign statements to constitute a user, and how do users sign statements to constitute a team? And we'll look into that with a little bit more detail. OK, how to define a user. So let's say Alice is signing up for this service, and she's creating her account. So the first thing she'll do is she'll pick a username, and then she'll start rolling a bunch of keys on her device. So she needs a signing key pair, which I'm going to just use this notation where lowercase s is the secret key and uppercase s is the public key. And she's going to need a Diffie-Hellman key pair for that device. So that's lowercase d, uppercase d. And this is potentially not obvious. We're going to build up for Alice something called a per-user key. And this is another Diffie-Hellman key pair, and it has a property that the private key, lowercase u, is going to be encrypted for all of her devices. So now she's going to sign her device public key with her signing key. She's going to encrypt that per-user key for her device. And a crucial property here is that the signing key and the Diffie-Hellman key for that device never leave the device. They're always going to stay on the device. And the encryption of this per-user key does leave the device. And when you roll this all up and post it to the server, we're going to say Alice has posted 3 SigChain links to a global Merkle tree. And what do I mean by that? So this is a Merkle tree that we're keeping for everyone who has an account on Keybase. So when Alice signs up, she's going to descend the tree to her particular leaf, and she's going to post 3 signed signature links. And they're going to have this property where whenever you add a new link, you sign also the hash of the previous link. So her first link is going to say, hi, I'm Alice. It's kind of a self-signed link. It's the first one. The second link is going to say, this is my Diffie-Hellman public key for my device. And also, I've made a per-user key because I'm just signing up. That's the third link. The hash of that third link is then bubbled up to the top of the Merkle tree. And that's now in more or less the public domain for everyone to see. So what does a new device addition look like? Well, let's say Alice started with her laptop. She's going to now add a phone. On her phone, she's going to generate a new key pair, S prime for signing, a new key pair for Diffie-Hellman. She's going to sign both devices with each other. She's going to encrypt her new Diffie-Hellman key with her new signing key. And this is the per-user key thing again. She's going to take the secret side of her per user key and encrypt it for her new device. And this yields 2 new signature chain links into this Merkle tree. Link number 4 is when she's signing both devices with each other, and link number 5 is where she's introducing her new Diffie-Hellman key for her new device. And what this looks like from the user's perspective is one of these flows where you take your new device, you take your old device, you take a picture of one with the other. And what that's really doing is it's sharing a strong secret between the 2 devices, as you can see in that barcode. And what that allows them to do is open an authenticated channel between each other. You don't really even need secrecy here, you just need authenticity. And that just means now the 2 devices know they're signing the right keys and they're re-encrypting the right per user key. Revoking a device is pretty straightforward from here. And as I said before, all these devices are equally powerful, so any device can revoke any other device. So her new, let's say she just provisioned a phone, that phone can now revoke the device that provisioned it. And so what that looks like is just signing a statement saying these 2 keys are no longer valid for me. The one thing that she does need to do is she needs to rotate that per user key. So the pessimal assumption is that the revoked device now has a per user key that's been compromised. So going forward, she wants a new per user key on her devices that hasn't been compromised. And this is this new U prime key that she's going to re-encrypt for all her non-revoked devices. So going back to the Merkle tree, what this looks like is you have a link where she's saying I revoke these 2 devices, and a new link saying I have this new per user key. And we can expose this to the user in a pretty easy to see interface. It's just more or less a button you could push saying revoke this device. And this is from my Keybase account. My phone will tell me there's a computer that I introduced at this date, I last used at this date, I push this button to revoke it. And there's one more thing we could layer on top of it, and this is where we got started as a company, and obviously we still feel strong about supporting, which is that Alice can, in addition to managing her devices, she can prove external corroboration of her account. So she can also make a signature saying, oh, I'm Alice on Keybase, but on Twitter I'm known as the real Alice. And she can then post a hash of that signature onto Twitter. So what that looks like from our Merkle tree's perspective is she's just making a new signature link saying, this is my Twitter handle. So to review, when Bob goes and looks up Alice, he's going to do the following operations. He's going to descend the Merkle tree to find Alice's leaf. He's going to fetch the tail of our chain of signatures. And so that's posted in the Merkle tree. He's going to play that chain back from the very beginning. And so that's going to be the first device introducing itself, provisioning the second device revoking the first device. It's going to be the sliding window of devices that eventually result in a picture of Alice that we could use today. And that's, these are the set of signing keys that represent Alice. These are the set of Diffie-Hellman keys that you can encrypt to. And this is her most up-to-date per user key. And in addition, she's also claimed these external identities. And so on our app, when my client goes and looks up Alice, in this case, the user Tammy, what my app is doing is it's doing those operations, and then once it's computed a cryptographic picture of who Tammy is, it then goes and checks those third-party services and corroborates that she actually had access to those services that she claimed to have access to. And so this is all happening on your phone and your desktop whenever you look somebody up. And this is the way we kind of solve that problem where if you want to introduce new people to your teams, you don't have to take the word of some servers that did like an email-based token exchange. You can actually, your device can check for itself that this is the right version of the person you want and not some imposter. So that was users. And what we're going to do is just build on top of that in a pretty parallel way to define what's a team. So let's go with the example where Alice is now creating, she wants to make a new cryptocurrency and have an ICO, so she makes her team called CoinCo, and it's going to have 2 admins. It's going to be her and Bob. So the first thing Alice does for CoinCo is she's going to roll what we call a new team secret. And this is, I'm just calling this lowercase t. And then she's going to run a whole bunch of key derivations to make other keys from that t. So she's going to generate a signing key for the team. She's going to generate a Diffie-Hellman key for the team. And also just a symmetric key for encrypted shared team data. So just 32 bytes of random data that everyone on the team knows that they can encrypt things for. And then she's going to take this seed T and encrypt it for all the users on the team. So when she's starting this team, it's her and Bob. So she's going to encrypt that seed for the per user keys of Alice and Bob. And this is again being put into the Merkle tree. And so obviously under a different path that's given by the name of the company. And the signature is going to be of the form, this is my company, these are the admins, and these are the public keys that correspond to my team. So adding a user to a team on top of that is pretty straightforward. So either Alice or Bob were signed in as admins, so they can now make additions or removals from the team, so they could add Chuck. And so there are basically two classes of users. There are those who are admins and those who aren't. And if you're not an admin, you get to see the secrets, but not change the membership. And what this looks like when Bob adds Chuck is he is going to add one more signature chain to that link signature link to that chain of signatures. And he's also going to encrypt the per team secret T for the new user Chuck. So link 2 is pretty simple. It just says, here's this admin Chuck. And finally, how do you remove a user? And admins can remove users, but when they do so, they must re-roll the team keys. And the assumption there is the bad guy who got kicked out, you don't want them to be able to access the new information that people on the team might add after they've been kicked out. So link number 3 in this case, where Chuck decides to remove Alice, is that you're signing a link saying, here's the removal of Alice, and here are the new public keys that correspond to this new secret that I just rolled for this team, and making a public statement as far as the team is concerned about the new public keys. So given this, we have to go back and revisit a little bit what it looks like when Bob or Alice revokes a device. And we said before, when that happens, Alice and Bob, when they revoke a device, they're going to re-roll their per-user key. But it's got to cascade up. And so therefore, whatever teams they were on, those teams also need to re-roll their keys using the same logic. But we kind of came up with a little bit of an insight into this process. This can be done lazily. So imagine it doesn't have to be eagerly upon device revocation. So imagine Bob is a member of 1,000 teams. One he uses every day, and another he writes to once a year. The one he writes to once a year, he doesn't have to run out and rekey right away. He just has to rekey it before the next time he'll make an update to it. So this actually really simplifies the implementation because we want to make it very easy for people to revoke devices and don't want to block that revocation on a lot of background rekey operations. So one of the key learnings in building all of this was this notion of a per-user key. And I say this as a key learning because version 1 we built without it. And so what does this system look like without a per-user key? I think the key operation to consider is what does it look like when Alice goes and provisions a new laptop. So imagine the whole system I just described, but where the team key is being encrypted for the user's devices directly and not the user's per-user key. So what that looks like is when Alice is pairing her two devices together, the one that already knows all the secrets, so we'll call it her phone, has to run out and re-encrypt all the secrets she knows for her new machine, the laptop. And imagine we have a case where, several cases in our system right now where someone's a member of 30,000 teams. And so that's actually a fair amount of work that needs to be on the critical path. And what happens is if Alice shuts her phone down or backgrounds the app before that's done, it turns out the new device is only partially keyed. And that is a really bad situation to be in because that device doesn't have access to all the data that the phone had access to. And moreover, this is like a viral contagion that can spread across the new devices. And so imagine Alice has a partially provisioned laptop and then provisions another machine with that one. That new machine in turn is only going to have access to some of the data that the original phone had access to. So that was more or less where we were for the first couple of years in this project. And we decided that this interior level of keys, this per user key, was really the solution to this problem. There's a whole bunch of other stuff that I'm happy to talk about either as part of question and answer or offline about what's going on in our system. One thing that's slightly interesting is that I said everything in our system kind of bubbles up to this Merkle tree. The easiest attack you could think of against that system is our server becomes rooted and we start showing one version of the Merkle tree to this side of the room, another version to that side of the room. This is called a forking attack. And one of the easiest ways you can think about solving that today is to just write that block to, or that root to some sort of global place. And we're using the Bitcoin blockchain for that right now. We write our Merkle root there maybe once every 4 hours, 6 hours? 6 hours, to prevent these so-called forking attacks. Something that's interesting is that the system I described, you could layer inside of it an ephemeral messaging system that's currently running and scales up to, in the biggest case in our system, a 2,000-person team. And so they're able to use ephemeral messaging pretty effectively. And we think that could scale way beyond that if it had to. And something that kind of we see on a daily basis is though we're trying very hard to get users to manage their own keys. And we do a lot of nudging. So when you sign up, the first thing we'll tell you to do is, hey, you have a laptop, how about provisioning a phone? And that's not only for their convenience, it's also so there's more ways for them to recover their account if they lose one of their devices. But this has been a slightly challenging thing to educate users on. They just, in some ways, they don't get it, and they need a lot of reinforcement as to how to manage their keys. Here's an example email I got not too long ago. Hi, Max. My server crashed and burned, and I lost my paper key and jalapeno. And I don't know about you guys. I have no idea what jalapeno means in this context. It's just the guy lost his jalapeno. Anyway, is there any way I could provide some sort of ID verification to get my Keybase account back? Thanks. So it's an ongoing process for us to try to get people to manage their keys properly, and we're going to continue to work on it as we go forward. So in sum, we think the key problem to hone in on here is what multi-device access looks like. And in particular, someone who's just bringing a new device online, do they have access to all the things they need to have access to? And the solution we cooked up is called this thing per user keys. But whatever system you happen to be working on, this is really something that needs to be correct if you want users to switch from their non-secure version of apps to their end-to-end secure version of, to the end-to-end secure version that you were building. In addition to that, I talked a lot about how users are chains of device additions, removals. And this notion where all devices are equally powerful seems to be easy to explain in the user interface, and also has some nice properties in terms of data durability and key durability. And finally, that same abstraction is pretty useful for organizing teams to be these chains of users, the admins of which are equally powerful. And then from there, you can build up this other abstraction, which is having a secret key that's rotated for a team in the right way. And that's really all you need to build full-featured apps that rival their insecure predecessors. So that's Keybase. You can download this app today on all 5 platforms. And we encourage you to do so. And also, thank you for listening, and happy to take your questions.
Okay, first question here.
Hi, thanks for all your work. I was wondering, what about the metadata in this Merkle tree, such as team membership? Is this something that your server knows? And do you plan to hide it somehow, or do you want to prevent your service from having access to that? Or?
Yeah, that's a great question. So our server knows it, yes. We hide it via access control right now. So if you have some secret company, you've shared the membership with us, but not necessarily with anyone else who uses the system. What does the system look like where the server doesn't know that? It's definitely a lot more complicated. In particular, we have to worry about badging and push notifications, and not fully certain how that would work without the server knowing about it. So we just didn't really go there. But
thanks.
Good question.
So if one of my devices is compromised and they use that device to revoke all of my other devices, how screwed am I?
Yes, you're screwed. You're totally screwed.
Thank you.
Our answer to that is you should have a good password and face unlock on your iPhone and a good swipe pattern on your Android phone. Great question. You got it.
So let's take that worst case scenario down a notch, and let's just say an attacker is trying to perform either espionage on the team. So their goal isn't to grief you, but they compromise one of your devices and they attempt to do a forking attack. So I've compromised maybe this person's laptop. I've installed malware. My goal is to split Alice off from the group and then maybe potentially relay messages to her, so she still thinks that she's talking to her team, but the group is now talking to Mallory, or Eve or somebody. What prevents that? Is it the Merkle pinning into the Bitcoin blockchain, or what's their attack window there?
Right. So that attack is better performed if you just take over our EC2 nodes, right? Alice's device probably might not be as useful because you really need to broadcast to the two separate groups separately. So
is it basically that her user key gets rolled whenever I attack her, and then other people on the team are going to be encrypting to that? Well, no, because I still have that key. So
I don't understand that.
Maybe we'll talk about it offline.
Yeah, but do you want me to answer
Sure.
The other question? I imagine Mallory controls our root passwords, and
sure.
Yeah. So I think the key data structure there is the Merkle tree, which Alice. If Alice sees one copy and Bob sees another copy, that means they've been forked, right? And so the adversary then has to maintain that fork indefinitely and can never rejoin them again. Yeah. And if Alice or Bob has any sort of offline gossip mechanism, or they're checking the Bitcoin blockchain, then they know they're on opposite sides of the fork.
Thanks.
Quick question. So I guess your view of PCS is some kind of active PCS in the sense that if something really happens, so the keys are static, but if something really happens that keys need to change, you change. Some kind of apps like Signal and so on, they take much more OTRs, they take much more aggressive approach, they try to rekey whenever they can in some sense. I guess here you can also do, even if nothing changes, you can just a device can roll a new key.
Yeah.
I'm just curious, what's your view of it? Are they paranoid, or maybe you're not paranoid enough? What's your view on very aggressively rekeying?
Yeah. Well, I guess our view is, we think the worst case scenario is that someone leaves a laptop. Well, a user leaves a laptop in a cab, or they lose a phone, right? And then we think maybe the key might be lost, in which case they push revoke and all the keys roll. So obviously there's a lunchtime attack maybe where someone is able to go in and compromise the key, and then we're not recovering from that. So I think we're putting a lot of the onus on the OS developers here, and they've done a really good job with local security of devices, and we're using that, I think, to prevent against these types of more subtle attacks where you still have the device, but yet it's compromised. So that's probably the answer we're taking. And in terms of, should I answer a forward secrecy question too, or did you just?
You could. It's related, but yeah, I agree with your forward secrecy.
Yeah. So our forward secrecy is certainly not as paranoid as Signals. I think we're rotating our ephemeral keys maybe once a day, so that definitely lengthens the attack window. But it's still, you should feel pretty good about something you wrote a month ago not being available to someone who compromises your keys today. So I think yeah, we're a little bit less paranoid than other people. And what we care a lot about is, I think, scalability. So we want to scale it to 10,000, 100,000 person groups, and we think that we've kind of made these trade-offs as a result.
And just another quick question: what about how serious are synchronization issues? Some of the issues, one device didn't update the key, didn't get this message, but things are encrypted with new keys. Maybe some message is lost, some update message didn't reach one device. How do you deal with this? Or you kind of assume reliable delivery of everything in order?
Well, my notion of you is up to date if I'm able to look at the Merkle tree and see what the last update you made to the Merkle tree is. And so in that sense, everyone is serialized. I think with ephemeral messaging, you might wind up, because that's another layer on top of it, and that's not synchronized with the Merkle tree. So you definitely could wind up in some cases where even though I ought to have been able to decrypt something, I can't because my device wasn't online at the right time. I think that's hard to avoid in all cases, and sometimes it happens.
But can you recover? I guess you will just rekey it, like in this case.
Can you recover? I think maybe there are some cases where you can't recover a message you should have seen. I think I'm not going to give you a great answer to that. But
we can talk offline.
Yeah.
Thanks.
Okay. Thanks, Evgeny.
Yeah. To me, it looks like I'll need to spend some time taking a look at the design. But can you delete or revoke the device from where you had signed in as a first-time user, because you're doing a self-signed operation there?
Can you revoke the device you're on?
From where you have signed as a first-time user.
Yes, you could definitely revoke the device you're on. I think that's allowed.
Okay.
But that wasn't the question? Sorry.
No, the question was from where you have signed up as a first-time user ever. For in the topmost, the bottommost element in the Merkle tree, or the first node in the Merkle tree down there.
Okay.
Where a self-signed operation was done.
Yes.
Can you revoke that device?
Oh yes, absolutely.
Because it's self-signed.
Yes, absolutely, yes. I think that's an important requirement because that happens in practice. I think I probably revoked my first device. You have this sliding window of devices that always speaks for you. And as long as that's a self-consistent sliding window, then it's fine in our system. Yeah,
okay,
good.
thanks. Great talk. Thank you.
Sorry, I didn't understand it first.
Have any search schemes been promising enough for you to look into implementing, or is that not something on the roadmap right now?
That's a great question. We have search. It works on the command line. It doesn't work in the UI. And it's doing the most basic, naive possible thing. So the clients suck down all the data. They just index it. They keep the index locally. We're not using any sophisticated encrypted searches. One optimization we could make is that your desktop could index your messages for you and sync it over to your phone, so that way your phone doesn't have to do it, but we haven't even done that optimization yet. We were a little bit scared of all the encrypted search technology because there's a lot of literature about how it's not working exactly as intended, so we didn't want to go there. But
cool,
thank
thanks.
you. Yeah.
Let's thank the speaker.
Thank you.
Okay, so we'll break for coffee, and the next session starts at 11.
Nice job. Thanks. 1, 1. Hi, everybody. If you could take your seats, please. We're just about to begin the next session. Yeah. Hi, I'm your session chair. Nice to meet you.
Good to meet you.
Thanks for coming. Yeah, I'll bring you up. He's just going to speak for a minute. Okay, we have a couple of important announcements to make, so if you could take your seats quickly, please, we'll get started. Thanks. Yeah. Okay, first of all, I'm going to give the mic to Nigel, who's going to announce how the lightning talk session is going to work. Okay, so Nigel.
Hello there! Right, I'm loud because I want everybody outside to realise something's going on so they can come in and listen because this is important. Okay, the lightning talks. If you have not been to Real World Crypto before, you have no idea what's going to happen. So please, neither do I, but this is what's going to happen. When the session finishes, there's going to be 2 talks in the next session. At the end of that session, which should be, I think, sometime, I can't remember what it is, I will look up. 12 o'clock, thank you. Right, so people will form an orderly queue. I'm English, we queue, right? So you queue here. The amount of time you will have to speak is the length of the queue. Is the amount of time left in the lightning talk session divided by the length of the queue. Therefore, if the people at the front of the queue speak fast, then people in the middle of the queue are going to get longer to speak. So there's a bit of a game deciding where in the queue you would like to be to get the maximum amount of time to speak. You are not allowed to use any slides. You just come up, you're given the microphone, you speak, I take the microphone off you when your allotted time has finished, okay? You give the microphone up when I say the time has finished. That's very, very important. And then leave the stage that way so you don't get in the way of the people queuing this way. Otherwise, it just goes like mad. So the speedier, the better. Orderly queue. And we'll try and get through everybody, even if at the end everybody can only speak for a second or so. They're the rules, and I hope you enjoy it. And you can do whatever you want. Use it specifically advertise jobs, brilliant ideas, things you just want to say. Just say, hi, I'm here, if that's what you're really interested in. But try and make it interesting. But anyway, over to Kenny.
Okay, thank you, Nigel. So that's starting at 12 o'clock, okay? And it's supposed to be lighthearted and fun and also informative. So we look forward to your participation in that session. We're going to move on with the formal part of the program now. Oh, one quick announcement before we do that. If you were looking for seating yesterday at lunchtime, rather than standing up to eat your sandwiches, we now have available behind this room the conference rooms on the kind of round the back of here. There'll be about 100 seats there. So if you want to take your sandwiches and go and sit down around there, that would be a nice place to have lunch. Otherwise, of course, you can just continue to use the rooms around here as we did yesterday. Okay, so that's lunch later on. Now we have 2 talks, and the first talk is going to be given by Jasper van Woudenberg from RiseSecure, and he's going to tell us about side channel attacks in practice and in theory. I hope, maybe. Maybe I misread your title.
Maybe.
Take it away. Thank you very much.
We'll know in half an hour. Right, thank you everyone. My name is Jasper van Woudenberg, and I'll talk about the practicing side channel attacks and fault attacks in a lab situation. Now, since we're a research community here, I also want to project our future vision here and all the research that we need to get there, to make it at least more interesting for me as well. So, our vision obviously starts with a connected toothbrush, as all visions do. Actually, this is my daughter's favorite connected toothbrush. But for now, just pretend that this is any kind of device, be it a phone, a smart card, a set-top box, anything that has security in it. We envision there's a big red button, although we're not hung up on the collar yet. And if we press that button, out come 3 things. Either a certificate that says this device is good or not. Maybe out comes a set of recommendations that say, hey, you should do this and this and this to improve it. Or even better, it would just automatically generate countermeasures for the developers. Now, we're not there yet. So let's have a look at where we are today. We have the toothbrush. Good start. But first, when we're looking at fault attacks and side channel attacks, we need to do some signal processing. So we obtain signals from this device while it's processing keys or anything other interesting. We need to do some leakage modeling, which means that we need to somehow relate these signals to the actual secrets that are being processed. And this is all manual work. I'll go into the more details in a second. Similarly, when we're doing fault attacks, we're actually trying to make a device misbehave in an insecure way. That can mean we hit it with a laser beam, or we glitch the power supply, or we temporarily overclock it. It doesn't matter so much, as long as it makes some kind of computational fault that we can exploit. And that can be during crypto, real word crypto, or it can be during, for instance, an access control check. If it's checking a PIN code, and at the end it makes a binary decision, yes, no, it's correct. And if I can flip that, then I'm also in. So it doesn't necessarily have to deal with crypto. So this is a large part of this is still art. And by art, I mean there's a human in a lab trying to figure out how to do this. There's not really a script for how to do this. There's some tools that you use, obviously. But it relies a lot on intuition and experience on how to really approach this. We do have somewhat of a button. So once we've done this signal processing, there's a couple of tools available to us that are kind of well-defined and written. So differential power analysis. We also have TVLA, which is, I'll get to that into a second, but it's another way of detecting leakage. And on the fault injection side, we have things like differential fault analysis, or just simply testing success rates of how well does my fault work on a device. So I'm going to bucket this as the science part for now. And on the right-hand side, we still have certificates that come out of our lab. We have recommendations that come out of our lab and countermeasures. And there's some science, some art. It's a bit of a mixed bag there. One of the challenges that we have with this is that this whole process for a single algorithm should take anywhere between 2 weeks and 2 months or so. So that's, especially on the 2 weeks end, that's pretty quick. So this is our motivation for researching this and making this more automated and making this better. So let's dive a little bit more into the details here. And we'll first look at the power side channel analysis and fault injection. And let's look at the art part of it. This is the piece of art that I brought for you. Stare at it and admire it. So it's a basic setup that we have in our lab. On the left you see an oscilloscope, which we use to capture signals. That big box in the middle is a power supply. And on the right, if you look carefully, I'll zoom in a second, you'll actually see a target device with an electromagnetic probe over it that we use to actually sense these signals. And the process kind of looks as follows. We take these signals, then we have to do a bunch of signal processing. We have to do the leakage modeling, and then maybe out comes the crypto key, if it's leaky enough. Now, signal processing really boils down to a number of tools, again, that we have, where it's not necessarily defined up front how to use those or when to use these. So this is really an art. For instance, if you have the top trace, it looks pretty noisy. And if you're an analyst with some experience, you can figure out, hey, if I filter it according to this bandpass filter, and then I do an envelope filter on top of this, oh, then actually I get a trace out like the bottom. And at this point, I don't even know yet if these are the right steps, because I don't know the right steps till I actually get the key out, yes or no. And the problem is, if I don't get the key out, then which of the steps that I took is wrong? I have no idea. So there's a lot of iterative processing going on here. Similar problems happen when misalignment occurs. So if I take many traces of a specific encryption algorithm, I see these traces, but they're never perfectly aligned, meaning that the time axis isn't always the same. Now, the problem that you see here is very easily solved by simple pattern match. But there can be complicating factors. For instance, if they are misaligned because the clock of the device isn't entirely stable, then I don't have sort of a static misalignment, but I have a constantly floating misalignment. Again, this is a problem that we know how to solve in isolation, but it gets trickier when we have noise and misalignment together. Because now we need to first filter, and only then we can figure out if we need to realign. So, two problems on top of each other. Then on top of that, we get something called points of interest selection. So if we have a huge trace, we can't always process the whole thing. So we kind of have to find out or guess at what point in time the crypto is happening. Again, we have tools to solve this in isolation. But now we have the problem of noise on top of misalignment, on top of point of interest selection. And these things are actually related to each other. Because if I don't filter, then I really am not going to see where my crypto is. But in order to find the crypto, I do usually something called a correlation, for which the traces need to be aligned. But in order to do the alignment, I need to have filtered things. So there's this weird mix of problems that individually are fairly easily solved, but solving these in general is kind of hard. And yeah, I don't know a good push-button approach yet. But that's not it. There's even more. So if we're doing this, for instance, in the EM space, what you're seeing here is a couple of different heat maps of signals that we acquired from a chip. And on this heat map, you see on the top, you see actually sort of ground truth leakage. So this is where we know the key, and we actually start looking at each position on the chip where it leaks. And in the bottom, you see the kind of unknown key approaches. For instance, we can look at the amplitude of the signal, how strong is it, on the bottom left. We can look at input correlation, which is basically where the input data to the crypto algorithm leaks the strongest, or on the bottom right, the output. But you actually see that these cheap ones, where we don't know the key, don't really relate to where actually the key is leaking. So now we might be going to the wrong spot. We do all those iterations of the couple of slides before, and we find nothing. So it could be we're in the wrong spot, we didn't align correctly, we didn't filter correctly, we didn't choose the right points of interest. It's a messy problem. So there's a few open research questions here. So first of all, how do you find good EM spots without doing t-testing? So t-testing is that leakage testing, which is quite expensive. And specifically, how do we automate that whole combined problem of filtering and alignment and points of interest selection, filtering? Non-trivial problems, very interesting to research. So on the fault injection side, well, like I mentioned, there's a few different modalities that we use. I put up a picture here of our electromagnetic probe. What it basically does is generate a huge electromagnetic spike, which causes a small current on the chip. That current, it wasn't supposed to be there, so it corrupts some computation. And then hopefully you bypass a signature verification algorithm or something like that. What we usually see in literature is attacking crypto with this. I would say 90 to 95% of the time we're not attacking crypto with this. So we're attacking things like secure boot or JTAG access. Because if you attack a secure boot of a device, you're in there early enough that you don't only get the keys, you get full control over the entire device. Similar with JTAG. JTAG is sort of a hardware debugging facility, which is usually locked down, so you use it during production or sort of manufacturing. You may use it during debugging, but in the field, on proper devices, it's fused off. But if you can glitch it back on, you're in the device. Everything is yours. So a lot of times we don't actually do DFA attacks in the lab. Now to show you a little bit of what we stare at as analysts, initially usually these kind of things. So on the left you'll see all kinds of parameters that we can tune. So you can imagine when we're doing a voltage glitch, you can make the glitch deeper, you can make it longer, you can do multiple glitches. With lasers you get similar parameters, but you also get an XY plane to play with. So there's a lot of playing and tuning that happens. And yeah, the output, this is actually quite a good output. Red means that we glitch something. Green means that the device is just operated as normal. Normally, you either start with all green or all red. Now you actually usually all yellow, which means I crashed. And then you have to tune, and it's a lot of, yeah, we call it finger spit, what do you call it? Experience and getting a sense of how to do this on the device. So also here we have a number of interesting open research questions. The first one is kind of fundamental, because we're in a lab, we don't like make chips or anything like that. We actually have no idea what's going on in that chip when we fault it. We have some idea, we have some hypotheses, and some things match our observations. But really what happens if you pulse, I'm talking about an electromagnetic coil of, it's about 1 millimeter in diameter. So I'm affecting a huge area of the chip. I don't know exactly what I'm doing, I just know I glitched past a certain instruction and then life went on. So going down to really understanding what happens, I think is really fundamental to creating countermeasures as well. Yeah, I think one other aspect that's quite important here is software scalable fault attacks. So you might be familiar with the clock screw work, or even the row hammer work. Row hammer, I assume you know. Clock screw was, I think, published 1 or 2 years ago. There they basically were able to, in software, overclock the CPU for a very short amount of time, cause a fault, and then be able to bypass. I think they were glitching RSA operations. But being able to trigger this from software obviously makes this a much more scalable attack. I don't have to go to a device with a probe and start generating strong electromagnetic pulses. So I think that's a really important area to study to make sure that there's no more of these avenues. So let's focus on the science part a little bit, just to show you that we do know some stuff. So what you see here is an overview of some statistics. And what we do is we take, in this case, an AES implementation, and we send it specially crafted input vectors. And these input vectors are crafted in such a way that, by using a known key, in round 5, the entire state collapses to a very low Hamming weight. So a Hamming weight of 2, 3 bits only set to 1, and the rest of the state is all 0. And we use that as an indication of whether the device leaks or not. If such a state has a very significantly different power profile than a random state, then we conclude that there's some kind of leakage going on. So we send this specially set of crafted vectors, we send a random set of input vectors. We basically take power measurements of both groups, average them, and then, or not actually average, we perform a t-test on them. And what you'll see in a leaky device is that, for instance, the mixed columns in round 5, there's a significant difference in the t-statistic, meaning, hey, there's some leakage going on here. You see this also propagate to other parts of the cipher execution. And this is a really nice tool in the sense that we use it in profiling a lot. Obviously, things need to be aligned again, because otherwise this trick doesn't work. But it gives us a nice statistics of where things are leaking, and by the size of the spike, how much it is leaking. But there's one big question here. How exploitable are the leakages that we detect here? So one of the things I need to do is I need to have a key in order to find this, and I find sort of arbitrary leakage. Whereas when I look at differential power analysis or correlation power analysis, I actually need to specify a leakage model. And that leakage model allows me to extract a key. What we sometimes observe in the lab is that we get these T-spikes, but we are not able to exploit them. And they can be pretty strong, but it just means either we haven't guessed the leakage model correctly, or maybe it's some kind of false positive. I don't know. So this is a really interesting topic to look at. Sometimes what you also get in practice is that in an AES engine as an optimization, only the first few rounds are protected, and the last few rounds are protected, and the middle rounds aren't. So I will still see a lot of leakage in the middle rounds, but I cannot detect the first few rounds, which is normally where DPA goes to. So, yeah, interesting food for thought. When I say DPA and CPA, I'm mostly talking about CPA, actually, which is correlation power analysis, which is already over 10 years old. And since then, there's been a lot of publications on different ways of doing power analysis. But we keep on falling back to our old tools. And it has a lot to do with performance, first of all. CPA is really cheap to calculate. And it also just seems to apply to so many different devices. So CPA has really proven itself to be basically usable across a lot of device classes. Whereas oftentimes when we see a new attack, obviously it's only tested on 1 or 2 devices. The improvements aren't always enough for us to invest and the time to go check whether the attack actually works, whether it goes over multiple devices, whether it's not too expensive. Remember those 2 weeks that we have to do this in? So we keep on falling back to CPA. So I think this is still a very open question in the sense that it's really hard to beat CPA. So can we find anything new there? Specifically with that time constraint in mind. Now, when we're looking at the science part of fault injection, it's usually statistics and visualization. So what you see here is a visualization of a voltage glitch. So we temporarily drop the supply voltage to a device, and we plot the response of the device in a color. So green means it operated okay, yellow means it somehow crashed, and red means we caused the corruption. And you see that there's a nice sort of sweet spot there that we, through brute forcing, have found. We've already developed a few more means to find these kind of spots besides brute forcing, because a lot of devices have this sort of curve, this trade-off between the length of the glitch and the voltage of the glitch. So you could instead follow that curve on the edge and sort of try to find that. Although it's not 100% generic over all devices, so we've also seen double curves and other funky things going on. Yeah, and this is almost, as I mentioned before, almost exclusively done on non-crypto, so on boot or on JTAG. Which also presents the question of how do we protect this JTAG and boot from these kind of attacks. For DFA, there's different ways to harden your crypto, but how do I harden conditional branch? We have some ideas, and we have some, you can do double checking, you can do randomizing of timing, but there's not a whole lot of research in this area on like how do we fundamentally protect this. Then on the sort of output side, we have certifications that we do. So there's always some kind of pass-fail criterion on certification. And interestingly, if you look at the practical schemes such as Common Criteria, EMVCO, Global Platform, none of them say this is the number of traces that you need to not leak your key in. Or none of them say this is the fault injection success rate that you need to be below. Actually, they go to a more, well, in my opinion, it's an interesting metric because it really goes to the attacker cost. Like how much time does it cost them? What kind of expertise do you need to throw at it? How long does it take? How many samples did they use, et cetera, et cetera. And in a way that's sort of as objective as we know how to make it, because number of traces sounds objective, but now think again about that art piece. So there's a lot of human intervention that happens before you get to the number of traces. So it's not as objective as it really sounds. So yeah, I think that's the open question. What is really like an objective measure? Because even if you look at time elapsed and things like that, there's still a human component in there. Yeah, in terms of improving products, we can usually deduct some information from our tests, like at what time does the leakage occur, how much leakage is there, what's the fault success rate, what type of leakage is there. But that's about it. So a designer really has to go back to sort of the clock cycle, sometimes the sub-clock cycle level, to figure out which part of his circuit is leaking. And that's a non-trivial task. Even more non-trivial is making this into countermeasures. Because I regularly see it turn sort of into a game of whack-a-mole. Because you push down one leakage and then somewhere else it comes back up and you're going like this a lot. So really, how do we automatically create countermeasures based on this test? I don't know, but I think it's definitely a worthwhile area of study. Another side note is that a lot of results in public are based on FPGAs or non-secure microcontrollers. These results don't always translate to secure microcontrollers or SoCs. These beasts are really noisy. They have a lot of countermeasures, so it's really non-trivial to study. So it would be really nice to have more results on that. What I also want to share is some of our current research that we do internally. We have multiple topics, but I can't fit them all in 30 minutes. But this one is kind of nice and recent. So you remember this slide? So we were doing signal analysis, and then we do some signal processing and leakage modeling, and then out comes the key. What we're actually doing is we're replacing that by a neural network. And we don't just want to get the key out, we also want to get some leakage info out and maybe some metrics on how well the resistance is. So we've been playing with this for over a year now or so, and so far the results are hopeful. One of the most interesting results that I picked here is that we actually managed to break/bypass a first-order masking implementation. This is based on publicly accessible traces from the DPA contest. And they have a countermeasure which is called rotating S-box masking. Basically what you do is you take an AES algorithm and you start masking, in other words, XORing with a random some of the internal states. And that way an attacker cannot make a prediction on the intermediates anymore, and that's supposed to foil DPA. Now this rotating masking, masking in general is expensive because you need to recalculate your S-boxes for every mask. So what rotating S-box masking does is it has basically a preset calculation on all the S-boxes, and then it just rotates through them. Now, what we find, and this is just to dazzle you, this slide. I won't go into all the details, but basically we have a deep learning network, and it actually manages to find some first-order leakage. So somehow this implementation is actually leaking first order, but CPA does not find this first-order leakage, nor does a template attack. So we're a little bit intrigued by this. But the nice thing for us is it was really a proof that this deep learning approach worked. We've also tested on misaligned traces and slightly noisy traces with the idea that convolutional neural networks are supposed to learn filters and are supposed to be invariant to translations. So it's one step in the direction of automation. On another side note, we rarely perform second-order attacks. Not because we can't, but because you need to combine several samples. And usually that's infeasible due to the noise that we have in these systems, so we don't really know which samples to pick, and the limited time. So there's really an open question here also on how to find those samples efficiently. We don't just want to break systems with deep learning, so we also are trying to analyze the network to figure out what is actually leaking. And we do this by sort of running the network in inverse, where we look at a specific Hamming weight leakage, and then we try to analyze which sample contributed most to that leakage. And if we do that for a whole bunch of traces, we basically get a leakage profile, as you can see in the bottom trace here. And the cool thing is it kind of relates to this t-test that we've also done. So there's some, at least anecdotal evidence that this is a nice way of working. Our conclusions for deep learning so far is that it can exploit and identify leakage. It does part of the artwork and part of the science, and at least it scales, because we don't, at least in theory. Two caveats at this point still. Hardware crypto seems to present a challenge. It's not that we can break it, but it's not working as well. And it still requires a network that needs to be tuned by a human, which is arguably easier than doing side channel analysis, but that's a bigger conversation. So other areas that we're active in is doing fault injection outside of lab conditions, so looking at larger distances or less control over the code on the device. Another really important part is design time analysis, as we call it. So we want to not do side channel analysis on a system, because then you have silicon and you're way too late. You want to do this while the designers are designing the circuits. Non-trivial problem. Similar with fault injection. So to wrap up, I think automation is needed for the scale of the issues that we're seeing in the world. There's a lot of interesting research questions on this. And am I still here? Yeah. And yeah, if you're interested in collaborating on this, please come find me. Okay, I think that gives me how many minutes for questions? Some questions. Some minutes for questions.
Science speaker. Okay, we do have some time for questions, so grab the mics. Maybe I'll ask one to get things started. So you presented the use of neural networks. That's one specific machine learning technique. Are there other techniques that might be more broadly applicable, or maybe these techniques would be themselves more broadly applicable to other kinds of attacks?
Yeah, that's excuse me. That's a good question. So machine learning really works, or at least the convolutional neural networks that we've used really work nice on signals, because that's sort of their natural habitat. One thing we've also thought about is we have this process of taking signals and having to decide whether we do filtering or alignment or selection. Maybe we can train a neural network sort of as in an agent way, where we decide what's the next step. Should we now do filtering or should we now do alignment? And then you can do reinforcement learning based on a t-test at the end to kind of reinforce certain steps. But that's just a thought at this point. We haven't actually tried this out.
So it becomes like an expert system or a side channel assistant or something, a proof assistant.
Yeah.
Okay, cool. Yeah. Any other questions or comments? Nigel?
Can you use the neural network? I mean, you talked about neural networks and you said, well, we're not going to do second order analysis. Why can't you use the neural networks to do second order DPA?
So you could. So in the training phase, what you're basically doing is you're giving it traces with a known key and basically a known Hamming weight or whatever a model is. You could extend this for a second order, where you train it with the known Hamming weight of, for instance, 2 samples combined. We just hadn't done that, and the key came out anyway. So that's why we haven't gone in that direction yet. But theoretically, yes, you could. Yeah.
Okay, if there's no more questions, then let's thank the speaker again, and we'll get ready. So just a reminder that after this session, we're going to have the lightning talks, and you have to form an orderly queue on the other side of the stage from where I'm standing, and then mayhem will happen, but controlled mayhem. Okay, so next up we have a talk on Tink, cryptographic library, and the talk will be given by Bartosz from Google. And we did test this. Do you have the mic? Yes, you do. Good. Okay, great. So thank you, Bartosz. Take it away. Is it switched on? There's usually a switch on the top.
Okay. And now it's okay? Yeah, okay, thank you. Okay, my name is Bartosz Przytatek, and I'm going to talk about a cryptographic library called Tink. It's a joint work with Daniel Bleichenbacher and Tai Duong, and with contributions by many other people. And so before I started, I'd like to thank also the organizers so giving me a chance to talk about this work. And one more slide, maybe to keep the expectation low. So I will not present a new crypto, sorry if I disappoint you. I will talk about new APIs, so maybe don't leave yet. And yeah, so why did we think that it would be useful to have a new crypto library? Well, we all know that cryptography is useful, but it's actually difficult to use. And especially if you are a developer and wants to do something else than crypto, but needs some cryptographic tools, it turns out that actually you're going to have a hard time using kind of the standard cryptographic libraries. You have to learn a lot of background to use them correctly, and also the APIs are complex, so before you can write a line of code, you have to read pages of documentation. And if you make mistakes, then some of them you will spot immediately, some of them not, and they can kind of pop up in the future. But what I mean by complex APIs. Let's take a look at an example of OpenSSL. I mean, OpenSSL is great, so it's nothing against OpenSSL or any other libraries that I'm going to mention here. It's more about that they are not suitable for the target audience of our library. So if you want to do encryption using OpenSSL, you probably encounter these functions. They have a bunch of parameters. Some of them are obvious, some of them not so obvious. And but keep in mind that doing encryption is a simple operation. You take, well, simple on the high level. You have some plain text. Maybe if it's an authenticated encryption with additional data, you may have some additional data, and then, and you would like to have a ciphertext, and that's it. So there are not so many parameters on the high level. Still yet, if you want to do this using this library, you have to have a bunch of parameters. And even more, some of them, it's not clear what they are if you are not a cryptographer. So like if you have an IV, well, what's an IV? You have to dig into it. You have to maybe some constraints on how you pick the IV. And also, in this context, you will also specify the key here, kind of in the clear text. And if you are debugging your code, chances are that maybe you will print some debugging info, and your secret key eventually might end up in the debug log. So yeah, it can end badly for you. It's not only about OpenSSL. So if you take another example of CNG, we have the same problem here as well. A bunch of parameters. Some of them are obvious, some of them not, and it's really hard to figure out how to use it correctly. Java, so it's not like it's only C++ issue. Java has some nicer surface, I would say. But so in a way, I can write all the encryption code on one slide or two. But you still have, again, the stuff that you have to care about. You have to know how long it's going to be the key, what was the IV, what's the size of it. You have to specify, okay, which encryption you're going to use. And if you want to change the encryption, you have to change your code because, well, you hard-coded your encryption mode in the code. And so, yeah, I said I can finish the encryption on 2 slides. So here's the end of it. So on the first slide, we set up all the parameters, and then we can do the actual encryption. But still here, we have to be very careful and know how long it's going to be the ciphertext for the particular encryption that we are using. So, yeah, so we could probably go over other libraries and spot some similarities here. But of course, we are not the first one that are struggling with this problem or notice the problem. So there are many efforts of fixing this, and one of them I want to discuss here shortly is Qitar. So Qitar tries to hide some of this complexity behind a more abstract interface, which is nice because then, yeah, you don't fill with all these bits. But what it's doing is especially in the hindsight now, it seems after years of usage of Keytar, seems it's, despite being so abstract and doing things on a more or less abstract level, the right abstract level, it's still not as extensible as it could be. So in the Keytar, we have this global, or the object, which is called Keytar, and depending on the context, how it was created, it can do some of the stuff. It can do signatures, or it can verify signatures, it can encrypt, decrypt. And if you have such an object, you can decide, okay, or you can figure out to what the object is good for by querying its purpose. But still, what happens if maybe the functionality that you want, the crypto functionality you want, is not present here in this API, in this function? Well, you would have to change the class. You have to add another purpose, and then make this change globally, and then recompile your code, and maybe it will work. It will work for your system, but not for the others. In Java, Keytar situation is a bit better because now the Keytar is a base class from which various functionalities are derived. So, for example, for encryption, we have something which is a derived class called encryptor, which has an encryption function, which encrypts the input and gives a ciphertext. But still, but then it blends in, and in a way, the abstraction went here too far because it blends in together and mixes various flavors of encryption. And then when you look at the code and see, okay, it's doing encryption, but then now you don't know, or is it doing public encryption, or is it doing symmetric encryption? And it might be important from the point of view, like want to understand what the code is doing to distinguish between these issues. And still, we have this global key purpose in them. So even if you would like to extend and have another derived class, you still end up, well, you have to have this, you have to extend also this key purpose in which, well, you can do it locally in your distribution and recompile the code, but then you get incompatibilities between various systems. Okay, so yeah, we probably could go over some other systems libraries, but instead of doing it, maybe I'll just tell what we are doing and try to convince you that it's going in the right direction. So in the rest of the talk, I will first state the design goals that we had. So some of them will addressing the issues that I mentioned. And then we'll actually directly dive into using things. So I'll give you show you real code that how you can use thing without much reading and without much preparation. After that, I will then go a bit more deeper into like how Think is built, and go over some of the points from our design goals, and show you how we address them. Finally, I will tell you what the status of Think is currently and what we plan for the future. Okay, so Think is a cryptographic library, so our first goal is security. So we want to provide API that is hard to misuse. So it's hard to pick parameters or provide parameters that would break the system that you are using. At the same time, well, crypto is complex, and they're kind of building everything from scratch would be a very ambitious goal. So rather than implementing all the crypto from the base, actually we are building on top of proven and well-tested libraries, so and we focus on the higher level APIs. The second goal is usability. Yeah, so we really want it to be easy for the users, so they should not study pages of documentation or have some background in cryptography to really use it. Because we want them to do their job correctly and focus on the actual functionality of the applications they are working on. Furthermore, we want also this readability. So when some security engineer or somebody will check the code that somebody else has written, it should be clear what the code is doing without digging too much into the context or asking the person, oh, are you doing here the right thing or not? And somebody already mentioned yesterday, kind of predicting is hard, especially for the future. We want it to be extensible. So we might some functionality currently, but we cannot foresee what functionality will be needed in a few years. So we want it to be easily extensible and without any kind of global enums, which are hard to maintain in the long run. And so that if you want to have a local deployment of thing, you can have some customizations that integrate with it easily without recompiling thing and without changing its code. Finally, we want to also have some built-in features which are common when we're using crypto. So crypto systems or crypto schemes are being broken or being deprecated, so we want to have an easy way to get rid of them. And also integration with external systems and services is very important to us, because current systems using crypto are getting more and more heterogeneous. So you have many platforms, many languages which interoperate together, so we want to provide this integration as well. Okay, so how a user of things will perceive it. So, well, roughly as cryptographers perceive cryptography on a high level through primitives. So what is a primitive? It's just an abstract representation of some functionality that we want to do. So it might be encryption, it might be authentication, some other. So, and the primitive is just a functionality defined in the form of the interface. It's not bound to any specific implementation, or it's just an interface of the functionality. What is nice about this is also that the implementations that we will provide for these primitives will come with security guarantees, so then when you look at the code, you know what's happening in the code. Yeah, so let me give you some examples of primitives. Well, let's start with a Mac. When you want to have message authentication codes, what do you want? You want to have two functions or two functionalities. First one, well, given some data, compute a MAC for this data, and given a MAC and some data, you want to verify that the MAC is correct. And that's it. You don't need anything else. For AAD, similarly, you want also two functions. You want to encrypt some data, maybe with associated data, and decrypt the data, if you are given ciphertext. And again, there is nothing more to add to here. So we have also some other more complex primitives like streaming AAD, where, for example, you are producing some data and you would like to write them in an encrypted form to some destination. So what you would like to have is kind of a stream to which you can write the data, and that the data would be automatically encrypted. So we provide here a parameter, the ciphertext destination where the ciphertext should go to, and then you get a stream to which you can write. It's kind of the encrypted stream. Whatever you write into the stream will be automatically encrypted. And vice versa, if you want to decrypt a stream of ciphertext read from some source, you get the decrypting stream. And there are some other primitives that we provide. I mentioned them later in the talk. But let's take a look. Okay, so how are we going to use it? And this is real code that would work. So basically, when you want to use crypto, you need some key material. So this would be the first step here. And for now, it's kind of abstracted. Just bear with me. So we assume that the keyset handle has some key material. So once we have the keyset handle in this, which contains the key material, we want to do something. So we want to get the primitive. So we will ask the keyset handle, okay, give me the primitive, and we'll specify which primitive we want. So we say, in this example, we want the AED primitive. And once we have the AED primitive, we can use it. So we can encrypt the plain text and get the ciphertext. And that's it. You don't have to pick any nonces. You don't have to pick any buffers and so on. So where do we get the key from? Well, it says, well, you can generate or retrieve it. So if you want to generate it, yeah, you can use some templates that we provide, but the templates then are meaningful. They tell you, okay, what are you doing? Or you can, and what parameters you are really using. And, or you can retrieve it. So you can retrieve it from a KMS or from other system that stores the keys. But again, the getting of the keys is really simple. So and it's kind of decoupled from the usage of the key. So you get the key material from somewhere, and then you are ready to use it. So now that we've seen that it's actually easy to use thing, so let's take a look a bit inside. So I explain some main structures that we use internally in Ting. So on the previous slide, you've seen that actually I have the key material in a key set, or on a key set handle, and I come to this in a moment, but let me start with something simpler, with just a key. A key is a container for a key material for a specific scheme, and this container is identified by a key type. So we sometimes call it key type, sometimes type URL, but it's just a string, and we have an example of the string on the slide, and it's implemented by the protocol buffer. So here for this ASGCM key, we just have some version which we use by convention, and then we have the key value. And that's it. There's nothing else in here. And it doesn't even say that actually that the key will be used for authentic encryption. So actually, the key itself doesn't say anything how it's going to be used. What does know how to use the key is associated structure, which is a key manager. It's a key manager. It's a class. It's an object that knows how to manage the keys of a certain type. And so there is an interface for the key manager, and in particular, the key manager will know, or given the key of this particular type, or I can give the primitive, and it knows to which primitive the particular key belongs. And also, and it knows also how to generate the new keys, given the parameters for the generation. So actually, we have this container for the key. We have the ASGCM key, and we have also the key format, which is a related structure. We just have the parameters for generation of new keys. Yeah, so we have roughly this structure. Also, we have various key types, and it's kind of one-to-one correspondence between the key types and the key managers. For ASGCM, we have the ASGCM key manager. For ESEX, we have the corresponding one, and for others, we have and as I said, the key manager knows what is the primitive that particular key type corresponds to. So in the last example, we are giving HMAC key, and the corresponding key manager know that actually this key is for MAX, not for AAD. So yeah, we have keys and key managers. So what are the key sets then? So key set is just a collection of keys. And what is important is that all the keys in a key set correspond to a single primitive, and the key set is a primary tool for the key rotation. And then the key set handler that you've seen in the example code is actually just a wrapper around the key set, so that we hide the sensitive data, so that kind of accidental logging of sensitive data to some debug logs or elsewhere doesn't happen. Now, so how it looks like. So given a bunch of keys, and all of them correspond to the same primitive. Is it 5? I thought it's still 10 past, no? Sure? Okay. 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 Okay, and then so we can pack them together into the key set. And in the key set, then we can wrap the key set around in a key set handle. Okay, so we have keys and key managers. We have key set and key set handle. How we put these things all together. For this, we have another container, which is a registry. And registry is just a mapping from key type to a key manager, so that when we have a particular key of some key type, we can ask the registry, okay, give me the manager for this particular key, and then we can do some stuff with it. And yeah, we can kind of register the schema manually, or we can we also provide tools to do it automatically. And this is really the foundation of how the getting primitives works. So you can do it manually, so you can ask the registry, give me the key manager, and then from the key manager you can get the primitive, or just when you call from this keyset handle, get primitive. Behind the scenes, what happens is that the keyset handle will actually contact the registry and get the primitives for all the keys in the keyset. So the registry is just really a mapping from key types to the key managers. And again, it contains all the key managers for various primitives. Okay, and so now it's given all of this setup, it's clear how, for example, key rotation will work. In a key set, we have this bunch of keys, and one of them will be the primary one, the distinguished one, which will be used to create the new crypto data, so new ciphertext or encryption, for example, or to generate new signatures. So when you have the key set, when you create something, this is where the primary will kick in. On the other hand, when you have some existing crypto data and you want to decrypt it, you will use all the other keys, or the primary as well. So there's automated matching between for example, the ciphertext and the matching key in the key set, and the one that matches will be used to decrypt. And also we provide some tools to disable obsolete keys. So sometimes actually you want to prevent usage of some keys at all, internally, so you don't want to even use them for decryption because you want to maybe catch some keys that you don't want to use, so you can disable them. What is also nice about the key set itself is that it provides a means of uniform handling for external keys. So I mentioned that the key itself is a container for the key material, but sometimes you don't even have access to the key material. The key material might be held by KMS, and actually you cannot download it, but you can only kind of query, you can use it, or in HSM. But this can be handled now uniform because the key itself now will not have the key material, but it's just a reference to the HSM. But from the point of view of a think user, it doesn't make a difference. It's just one of the keys in the key set. And it will work the same for the key rotation and for encryption decryption. And what you can also do is using the registry, you can do this gradual deprecation of cryptographic schemes that you want to get rid of. You can, for example, say that, well, you still want to use it because you have some existing keys and some existing data, but you don't want to create new keys. And so you have kind of the full control over that. Okay, so if you recall, I was saying some of the design goals. One of them was readability and auditability. So now when you look at the code that does use thing, then it's more apparent what is happening in the code. So if you see that you have an AAD, and you call the AD encrypt, then you know, okay, this is symmetric encryption with authentication, and then you kind of can decide, oh, is it the right type of encryption in this context or not? Similarly, if you see the hybrid encrypt, you can say that, oh, this is the public key encryption that we have in here. Is this the right one to be used here or not? And also the kind of the concentration of all the key managers in the registry gives you the power to decide or to audit or to see what kind of schemes your application is using. And we don't support it yet, but we are planning to add also like some statistics, because maybe your application is kind of mostly using kind of the new stuff, but maybe there are still some data around that occasionally you need the old keys for. So then you can do the tracing and analysis. Okay, how important the old scheme is? Should I still keep it or not? Okay, so let me move on to the kind of last part that I wanted to highlight from the design of Think is the extensibility. So, of course, so we provide some primitives as abstract interfaces, and some implementations, but it will not fit everybody. And like if a company has some existing systems, is using some kind of encryption, we will not be able maybe to provide it, but then you can do it on your own and quite easily. And looking more into the future, As I said, we cannot foresee what kind of crypto primitives you will need in the future. But again, adding them to the to think is easy, and you can then take the advantage of all the mechanisms that work for the standard components of things. So let's see how you would add, for example, custom implementation of AAD that would work with thing. So, you would have to define the container for the key, like the key type. So actually, you would have to have these two containers, one with the my custom key, and the other would be the custom key format, which would tell how the new keys are generated, what kind of parameters you need for that. And once you define these containers, you have to implement the key manager for the custom key type. Due to the templating, actually, you won't have too much work because so many of things will happen automatically. But still, you would have to do some things, but so you have to implement a few methods. But as you see, so here you would say that, okay, that your custom key manager will output instances of primitive AAD, and then it will use your custom key. And then, you have to say how the key is used. And once you implemented this custom key manager, you can register the custom manager to the registry or put it into the registry. And then from now on, you can use it as any other implementation of AAD. So then all the key rotation stuff works as for the others. Now that was pretty easy. What about custom primitives? So like if you want to have some functionality about which we didn't think about. This will actually also happen in 3 simple steps. Well, you have to define what's your primitive. So, it will do probably some crypto stuff. So you say your primitive has some method 1 or 2 or more. So in this example, we have just one. Well, it does some crypto computation on input and gives some output. So once you define the primitive itself, there's one more structure that you have to provide, which I didn't mention before because it's kind of internal detail, but it's still relevant in this context. It's a primitive wrapper. What is a wrapper? A wrapper is just a kind of container for all the primitives that you have from a key set. So if you have a key set, you have several keys inside. And when you instantiate primitives from these keys, you would get a bunch of the primitives. So for example, you have a bunch of AADs, but a bunch of AADs is not an AAD itself. So you have to wrap this thing. So you have to kind of do this selection of the primary, like to create new handling of the primary primitive to create new crypto content and use the other primitives that you get from the key set to handle the existing crypto data. But in most cases, it's actually also pretty simple. And once you implemented the primitive wrapper and registered it also, then you implement the key managers as on the previous slide, and then from now on you can use everything as previous or as standard thing primitives. Okay, so I hope I convinced you that there are some simplicity and some use of thing structure and thing as a tool. So let me tell you where we stand right now. So Think is open source on GitHub for over a year now. And we do support a bunch of primitives. In addition to the ones that I discussed, we also have the deterministic AAD, and I think I didn't talk about the digital signatures. And it's available in several languages. So far we released it for Java, C++, and Objective-C, and it's working on Linux, it's working on Android, it's working on iOS. In preparation, we have Go, JavaScript, Python. There is also a community-driven effort to provide support in PHP. And of course, all of these implementations are kind of compatible. So you can do encryption on one, decryption on the other, and it just works. And we have also integration with KMS systems. So for Java, we have already that for AWS, for Google Cloud KMS, and for Android Key Store. For Objective-C, we support Apple Keychain, and for C++, we'll also support the KMS systems pretty soon. And maybe before I say summary, I should say one more word. So actually, the thing is open source, but it's used by many systems at Google and also by third parties. And it will be more and more in use. So I said it's used by Android, by many Android applications, and also like on server side at Google as well. Yeah, so I talked about the thing as a crypto tool, actually for those who don't want to do crypto in a way, but have to. It's supported in multiple languages, multiple platforms. It has many desirable features. There's actually many more features that I didn't talk about due to the time limitations, like threat safety, protections against side channel attacks, and versioning, and so on. And last but not least, it's open source, and we do accept contributions from the outside world. So thank you very much.
Thank you. My apologies about the timing error.
No worries. Yeah.
We have time for questions, so please come to the mics.
Hello. In one of the first slides, you showed that for AEAD, you have a streaming API.
Yes.
A streaming encryptor and streaming decryptor.
Yes.
When you are decrypting, do you stream the data as it comes, or do you buffer everything? Because if you do, before you have verified the MAC, you cannot be sure that the data is correct. Mm-hmm. And you have to read all the ciphertext and the MAC to verify it before beginning to return the data to the application. Or the application must take care to verify ultimately with the cloud that the MAC was correct and everything.
So with our interface, so implementation of the interface, actually, like when you get the output, it is authenticated. So you don't have to kind of do on top of this your manual checks. Yeah.
Okay, so it's just syntactic, but actually it buffers everything and do everything right.
Yeah.
That's it. Yeah. Okay, thanks.
What are the obstacles for other language support, for in particular strong type languages and more secure languages like Go, Rust, etc.? I mean, those haven't been your target, and I was just kind of curious, like, what's keeping you from having those be a target?
Well, so we are working on Go and some other languages as well. I mean, it's more less kind of we are demand-driven. So if you have projects that need some support in some particular language, we do provide this. We have limited manpower, so that's why we have to kind of pick and choose. So ideally, we would like to provide every language to the same extent. So I think I didn't mention, but the support in various languages differs. So it's not like that we currently support all of the implementations in all the languages. So the Java is the most advanced one, but others are catching up. And so there is no like intrinsic reason why we don't do it. It's just kind of resource management. Yes.
So related to your statements about other language support, like obviously there's limited resources available to you. There are many projects that would be potentially interested in integrating these sorts of constructions, as you call primitives. Right now, those primitives are described obviously in high-level user like descriptions where you say, oh, it's 0882 and things like that. But the only information about how it's actually, like what the actual format is the implementation. Do you guys have a plan on like building more formalized specs with test vectors so people who might want to build it for their own languages and their own libraries are able to interoperate with you?
Like we don't have the code is documentation in a way, and it's kind of stable. So we will not change the format now that we have kind of many customers in Java and C++. But even if you would do that, like we have the versioning that I mentioned, so we could do that. Because the key managers would say that we require some version of the key manager, and so kind of we could support the old one and the new one, so we could change the formatting as well. So we don't have to abandon anything. So it's also extensible in this way. But to answer your question, whether we would provide the specs, I think we could kind of write down a few specifications, like extract it from the code and tell what it is. Talk to me, and if once we have it, also we will put it on GitHub as well. But if you are more closely interested, just talk to me, or talk to Tai, who is sitting in front, like here.
All right, thank you very much.
Okay, any more questions? Okay, and let's thank the speaker again. Thank you very much. Just before I unleash Nigel, let me just do a quick temperature check. Is anybody else cold in here? And is anybody too warm? Okay, I think the cold-blooded people have it. So we'll see if we can get the temperature turned up. And now it's over to Nigel.
The warm-blooded Nigel. So, we have one person in the queue. You've got 50 minutes. Okay, right, so let's, okay, so we'll wait a bit. 1, 2, I've got to do some maths. I'm not very good at this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. 18. Okay, we're currently at about 2 minutes a pop. About 2 minutes a pop. I've got to turn my phone on. It keeps going to die. Right. On your marks. Get set. Go.
Hi, my name is Vipin Bharathan. I have 2 points to make. One is about blockchain. I heard some deprecatory remarks about blockchain. I believe it's because of incomplete understanding of the abstraction rather than real problems with it. So I urge you guys to look further into it before bashing it. Okay, that's the first thing. Second is I work with a group called Hyperledger, which is we incubate like 5 or 6 different DLTs, and I'm the chair of the Identity Working Group. So I would urge any participation by the cryptographers in that group, because we really lack that expertise there, and your contribution will make a big difference. So bang for the buck. The second thing is there is a library called URSA, which is a cryptographic library being constructed right now, so any contribution to that will also be helpful. You didn't have to take the mic from me.
Brilliant, very good. That's the kind of talk we need. So give him a nice round of applause. Woo! Right, okay, so on your marks, get set, go.
Whoa. Hi, everyone. First of all, 2 seconds to say thanks to the organizers. This is a truly great conference. And I'm just going to say my name is Daniel Benarach. I work at a company called Kedit. And I guess like a year ago or something, we realized that the whole zero-knowledge industry is actually growing pretty fast. Related mainly to DLT and blockchain space, but not necessarily. And I essentially wanted to talk to you about this initiative that was started last year called ZK Proof. So Zero Knowledge Proofs, it's zkproof.org. You can check it out, and it's essentially an open initiative of academia and industry to standardize the use of zero knowledge proofs. So standardization is very important in cryptography. I guess we all know about it. We've heard about it here. Essentially, we are at the point where we want to create a set of community standards that essentially are going to be used as guidelines for people that are joining the industry, from the theoretical level all the way up to the practitioners and the developers. And essentially, we're planning a second workshop that is going to happen in April in 2019. April 10th to 12th. We welcome everybody to register, to come participate. We have opened a submission process for proposals related to zero knowledge proofs, as well as for some kind of contributed talks. So if you have work on zero knowledge, definitely submit this and propose a talk. I'll just say the steering committee today is composed by Dan Bonnet, Ran Canetti, Shafi Goldwasser, Alessandro Chiesa, Yael Kalai, Jens Groth, Yuval Ishai, Mutu, Erin Kintasubramanian, Elaine Shiv, Viv Zohar, and Eran Trommel.
Thank you very much, and go.
Hi, my name is Greg Rubin. I work for a tiny little company called Amazon, and have been there since 2005.
The team I'm on is something called AWS Crypto Tools. Our goal is to make all of your crypto problems go away so you don't need to worry about them, or your developers don't need to worry about them, and can focus on what actually matters. Or as I like to say, we write crypto so you don't have to. We own the AWS Encryption SDK, which Matt Campagna talked about earlier today. We also own a bunch of client-side libraries for encrypting data that integrates with AWS services. And we're working on a lot of other things, including many generic tools that don't directly interact with AWS, and plan on launching them in the future. So why am I up here? We want your help. We've got a GitHub account. We do pay close attention to what's going on there. We want to know what you need. We want to know how we can help you, what we should be building for you. We want your review. We do a lot of review. We hire people to do our code reviews. We want extra eyes to make sure we're doing this right and not delivering sharp edges to developers. We also want plugins. We want to support different key management systems. We want our code to interoperate with other systems that we don't even know about, so that they can use our systems and that things just become easier in general. So please come talk to us. Please come help us. We'd love to chat with you. I'll be around. Most of my team is around too, and they're all amazing people. And finally, because I think I'm technically required to say this, yes, we're hiring. Thank you very much.
Thank you, and go.
Thank you. I just want to make a couple of announcements about some of the work I guess we've been doing at NYU about secure messaging and random number generations. So definitely talk to me. I won't be able to tell kind of any significant details, but in terms of secure messaging, we gave, I think, the first analysis of the signal protocol, which is kind of cryptographically sound. The definition is clean, it's parsable, it applies to the real signal protocol, it formalizes properties such as immediate decryption, and hopefully it's understandable, it's modularizable, so you can do post-quantum signal. If you're interested in doing post-quantum signal, talk to me. And I feel like this kind of the definition could be easily extendable to the MLS group, so I'm planning to attend the MLS meeting, and hopefully I'm willing to learn, hopefully we'll learn a lot of things from that, and hopefully also contribute. So definitely talk to me if you're interested in aspects of secure messaging, how to define, extend it, and so on. And the second announcement, I want to talk about an upcoming work of mine that I'm very excited on random number generators. So for the first, it's kind of an embarrassing situation that unlike encryption, authentication, the state of standardization and utilization of RNGs is kind of embarrassing. So I think, so now we finally have the right kind of models, the right definition under which we can analyze practical kind of RNGs built on cryptographic hashing, which don't have seeds, and yet they provably kind of accumulate and extract randomness in a good way. So if you're interested in enjoying standardization or build kind of a good RNG which is not only practically secure but also theoretically sound, please talk to me.
And thank you. And go.
Yes, my name is Christopher Allen. I'm best known as being the co-author of TLS 1.0, which I hope everybody here knows you shouldn't be using anymore. I hope that in the future I will be best known as the architect of the decentralized identifier. What is a decentralized identifier? It's a new architecture to address some of the fundamental problems that we have as protocol and cryptographic engineers. I know a lot of you may have heard about it in various forums. You associate it with blockchains. Not all decentralized identifiers use blockchain technology, but they all use cryptography. This has been moving forward. It's been incubated for the last 3 years at Rebooting Web of Trust. It's been in the last year at the W3C Credentials Community Group, and it looks like it's going to be formally ratified as a working group at the W3C sometime this spring. So I really encourage you to take a look at it. If you have skepticism because you've heard of its association with blockchains, take a deeper look at it. The spec is up in an early draft form. There are over 20 companies, I think, at this point that have implemented various versions of it. It's a very powerful architecture for solving some problems. It including things like anti-correlation, pseudonymity, and just the decentralized problem. So Credentials Community Group at the W3C has the current spec. Rebooting Web of Trust is March 1st through 3rd in Barcelona if you want to meet with other people to work on it. And I'm with Blockchain Commons, which is trying to fund vendor-independent and blockchain-independent development. Thank you.
Thank you very much. And go.
Hi, my name is Brent. I work at Evernym, and it's been 3 days since I last used blockchain. My blockchain usage started pretty innocently. Just some guys messing around with hashing, you know. A little MD5, a little SHA-1, and then a cryptographer turned us on to collision-resistant, cryptographically secure hashes. And it was a slippery slope from there. We were into Merkle trees and Patricia trees, and we would prove set membership using, you know, knowledge of the root hash. Somebody brought in proof of work. And a little bit of PBFT, and before I knew it, we were doing consensus. We called it a distributed ledger, but we all knew what we were doing. I dabbled a little bit in secure multi-party computation before my eyes were opened. I knew that if I wasn't careful, I would find myself doing an ICO. And it was a rough come down. I still use blockchain, but only because it's prescribed by my use case. And I'm proud to say I haven't abused it in a long time. I want to thank the organizers of this conference for creating a safe place where crypto does mean cryptography. Thank you.
That wins the coolest talk so far.
So I think I picked the best spot in the queue because I'm about to deliver a DLT job ad after that talk. That's a lot of fun. So I work at a company called Digital Asset. We use crypto since we are a DLT company. We are supposed to become real world by 2021 at the latest because by then essentially every stock trade in Australia is supposed to be processed by our systems. So our take on DLT is, I would say, a little bit different than other people's. So our main product is a language for modeling business workflows across multiple parties. And then on top of that, we build a platform that it's like a distributed runtime for the language. So the language is pretty high level. And the goals of the platform are to secure its execution, so we have pretty interesting problems such as assuring integrity while preserving privacy. And we have to build crypto protocols to do these things. So if you're interested, we're looking for cryptographers. We're also looking for formal methods people. So I'm one of them actually. I have a background in formal methods, and there's a few other such people in the company. If you're interested, come and talk to me. We have locations in Zurich, Europe, Switzerland. We have London. We have Hungary. Here we have New York in the US. And we have Sydney as well. So that's pretty much all I want to say. Thank you.
Thank you very much. And go.
Thank you. Hello, my name is Sergey Gorbanov. I work on cryptography at Grant, and I'm a faculty at University of Waterloo. So today I just want to tell you briefly about a BLS signature scheme and our effort to standardize it. So BLS signature scheme was introduced by Bonet, Lin, and Sachem almost 15 years ago. It's a signature scheme that uses pairings, and it has very nice efficiency properties, and in particular aggregation over the signatures and the public keys. So we think there is a big need for the signature schema. In particular, it can help to optimize some of the classical internet protocols, such as BGP, as well as newer internet systems, such as your blockchain. So together with Dan Bonet and Hotek Wee, we initiated an effort trying to standardize this signature scheme. There are in particular a few trade-offs that one needs to make when instantiating it, and we think it's important to make them clear for developers. So currently we're planning to submit a standard to the CFRG working group. If you're interested in working on this or contributing or helping in any way, please let me know or send me an email. We'll be happy to talk with you about it. Thank you.
Brilliant, good.
Hi, my name's Jeremiah. I'm the founder at Subspace Labs, and we are building a decentralized database protocol, and we're trying to hire a real-world cryptographer. So we are basically building a decentralized database as a service that would be equivalent to something like Google Firebase, but has a decentralized backend. So the point is to make it easy for developers to build applications where users can own their data. So we recently received a National Science Foundation grant, and the funding is going towards hiring a cryptographer full-time. So if you have an interest in proofs of space and time, distributed hash tables, distributed databases, and of course blockchains, please come talk to me. Again, my name is Jeremiah with Subspace Labs. Our website is subspace.network. Thank you.
Thank you. Thank you very much. We're now back on schedule. Off you go.
Hi, my name is Jonas Akers. I'm here hoping someone here likes to break things. I work on an open source project called EasySafe. EasySafe is a distributed encrypted file system that you can mount from anywhere with zero configuration just from a passphrase. So you type a passphrase on your workplace computer, you've got an encrypted file system, you want that at your house, you type in the same passphrase, you don't need any IP addresses or anything. The data is only stored on your computers, but they find each other anyway. If you think you can break it, go to easysafe.io, and there's a full write-up of all the cryptography and relevant information, and I'm hoping maybe somebody could take a look at that information and try an attack. Anyway, thank you very much.
Excellent. We're really motoring now, so...
Hello, I'm Robert Lee. And I'm from Crypto Quantique. We're a security company based in London in the UK. We've developed the world's first quantum-driven security chip in silicon, and it provides a large, unique, and unclonable key space. And with this technology, we're currently trying to build security solutions and products with which to secure the IoT. And I'm here to announce that we're hiring. So we're looking for people to join as cryptographers, developers, and we're also looking for a few more chip designers, if you know any. So I'm going to tweet the job descriptions on the hashtag. They're also up on our website, cryptoquantique.com. So if you're interested in what we might be doing or working for us, just come and find me. I'll be around for the rest of the conference. Thank you.
Thank you very much. And go.
Hi, my name's Scott. I work for Paragon Initiative Enterprises. So I'm here to talk about PHP. Now, this is not a popular language at conferences like this, but despite that, according to W3 Techs, it powers about 80% of the detectable web servers on the internet. And this is a little software written in PHP called WordPress that powers anywhere between a quarter and a third of the internet. And despite these statistics, it doesn't get a lot of review from the cryptographic community. WordPress has this feature called automatic updates, where they try to release security updates and get them applied across the entire ecosystem immediately. However, it's protected from the update server by a header called content MD5. So part of what my company does is we work with open source software projects to try to make them more secure. We tend to focus on the PHP community because that's like the punching bag of the InfoSec community. And work is currently underway to get ED 25519 signatures to land in WordPress 5.2. Beyond that effort, I want to include another initiative to add plugin signing, which adds another layer of complexity. However, I have an implementation I call HERD. It stands for Hash Ensured Replicated Database. It's also a reference to herd immunity, which is what automatic updates provide for an ecosystem. It basically uses a local database synchronized based on updates to a cryptographic ledger. It's not a blockchain. It uses Blake2B in a hash chain structure, so I call it Blake chain. So if anybody is interested in this kind of open source collaboration, feel free to find me and tell me your feedback. Look it up on GitHub. Our company's website is paragonie.com, and we are at github.com/paragonie. Thank you.
Thank you very much. And over to you.
Hi everyone, my name's Sam. This is my fourth Real World Crypto. 3 years now from when I was on stage presenting our formal analysis of TLS, which means that I earned this TLS swag with a lot of loss of sanity, basically. This is now my first year from making the jump from academia into the real world. I'm currently working on building out a startup to help companies to secure their infrastructure by providing like a unified authentication authorization layer. If this is something as a company you're kind of interested in improving, working on, or you just have some experience that you would like to share with me, I'd love to hear from you. You can either get me at sam@Keish, KEE.sh, or I'll tweet a link as well, and you can come find me at the conference. Thanks very much.
Thanks very much. And over to you.
Hi, my name is Apurva Deshpande. I'm a PhD student at Brown University, and today I want to briefly talk to you about what I think is exciting new work. So cryptography has always challenged the limits of what we believe is possible. With zero-knowledge proofs, we can prove that we know something without revealing what it is that we know. But what if we want to prove that we don't know something? That's a paradoxical question. What if we want to prove that we are ignorant of something? So in recent work, we have introduced the notion of proofs of ignorance, how to prove that you don't know something. We give a formal definition of the same and construct proofs of ignorance for a subclass of languages. This is a joint work with Yael Kalai at Microsoft Research and MIT, and our manuscript is up on ePrint. So I want to briefly give you some intuition about this. Let's say Alice has a locked box, and Alice wants to prove to Bob that she doesn't know the contents of the box. Right? So Bob has no reason to believe Alice in general. But if Bob knows that Charlie gives away locked boxes, then all Alice has to prove is that she got her box from Charlie. So in some sense, not knowing something is a proof of knowing something else. So in context of NP languages, we want to be able to sample an instance and prove that you don't know the witness. This is new work, and the reason I am talking about this today.
There we go. And the next one.
Hi, my name's Hunter Fryer. I'm the lead on Google's Cloud Key Management Service, and I'm not going to talk about that. I'm going to talk about my passwords, because I actually have a password generation scheme that I like and I want to plug. I think a lot of people are familiar with the correct Torse battery staple method of just coming up with a list of words. I think that works great. The problem with it is that they end up being really long. Like I would sort of sometimes have to type my password in front of people, and people would be like, Jesus, that's a really long password. So to be very pedantic about it, like the entropy is good, but the entropy per character is pretty bad. There's this really nice word list, actually, that's included in the Bitcoin improvement proposal number 39, which has this cool property that it's 1024 words that are common English words that the first 4 characters are unique among all the words. So the approach that I've been doing recently is just pick 5 words off the list, take the first 4 characters of each, stick them together, and you actually get good, lower bound on the entropy, and it works well. I just, during the last talk, made classypasswords.com, which is a single-page HTML file which will generate a bunch of these passwords for you. If you go there right now, you'll see an SSL error because I just set it up. But after a little while, oh, it's working now? Okay, cool. And you'll see typos and stuff like that, so it's great. So if you don't like your passwords, or you know somebody who really should use better passwords, and you want to just say, here, do this, please consider doing that. Thanks.
Thank you very much. And go.
Thank you. Hi, I'm CEO Chow from Purdue University, where I work with my PhD advisors, Ninghui Li and Aniket Kate, which I believe is in the audience, and I cannot quite find him, which is a textbook definition of, I guess, K-anonymity. So in general, I'm interested in bug finding and reasoning about software implementation. And this is my first time attending RWC. And by RWC, I mean Real World Crypto, not the Rugby World Cup. Maybe one day I'll go there. So I'm going to take this chance to do two shameless self-promotions. First, one of my recent work found several bugs that enable new variants of Bleichbacher's low exponent RSA signature forgery, which is amazing because it's already more than a decade since Crypto 06, where Bleichbacher gave his original attack. Anyway, if you're interested in this, please try to go to NDSS, which I'll present this work. And if you cannot go to NDSS, a preprint of my paper is already available on my homepage. And second, I'm in the job market this year, so if you're hiring, please feel free to ping me and see what we can do. Thank you.
Okay, and the next one.
So I feel like we're going too fast through these, so let's just take a minute to think about trees. Okay, enough about trees. I'm Catriel, I work on MLS, among other things, but I'm not here to talk about MLS. I'm organizing a London Crypto Day, which hopefully will have a feel a bit like this, but will be significantly smaller. Formal announcement to come, but if you'd like to come, or if you don't think you'll be on the mailing list, come find me. It's going to be on the 7th of March. It's going to be in London. Thank you.
That was super fast, so over to Dan.
All right, I have a question for the audience. How many people here have ever flown on United Airlines? Let me see a show of hands. How many people of you would say you enjoyed the experience? Yeah, one person raising their hand. That's clever. Yeah, so this is a little talk about one small piece of the United experience, which is when you're crammed into the seat and then you ask the flight attendant for like some whiskey to try to forget the rest of the United experience, and then they hand you this tiny little bottle and say, that'll be $10, please. If you are going to be flying United this month and you're worried about this part of the experience, then I have a little bit of help for you. Tanya and I have a bunch of these little vouchers, which are each, until the end of the month, on United Airlines, worth one drink. And it's first come, first served, so don't ask us what they did to us to make us get these vouchers, but we got a whole bunch, so come to me. I'm DJB. Tanya Long also has some, so that's it. Thanks.
There is an offer you cannot refuse. Go, yeah. You'd want to buy your United tickets now just for that, don't you? Okay.
Hi, I'm Gary Belvin. I am the technology lead for key transparency at Google. Key transparency provides authenticated key discovery for end-to-end encrypted applications, including Google Duo launching sometime. Key transparency and its underlying Trillion technology are all open source and easily composable into a variety of authenticated data structures, including certificate transparency, binary transparency, gossip, and a number of other things. You can go find them all on GitHub or keytransparency.org.
Thank you very much, and over to you.
Hello, I'm Karl, and I work with ShareMind MPC, which is a secure multi-party computation platform. And yesterday I was talking with some people and I didn't even know if I can reveal that. But today I got a word that I can reveal and announce it, that we have put together a set of documentation for ShareMind MPC. It's available at docs.sharemind.cyber.ee. That's all. Thank you.
Don't leave the stage. Don't leave the stage. Don't leave the stage. Okay, leave the stage. We want to thank ShareMind and all the other participant companies that have actually sponsored the conference. There's been a number up here already with Algorand, ID Quantip, blah, blah, blah. There's been loads of companies sponsoring the conference. So thank you to Cybernetica and all the other sponsors. Thank you. And if you are working for a company, come up to see me, give me your money for next year. Right.
Hello, my name is Bartosz Przyjatek, and you may know me from a talk on cryptographic library called Ting. I wanted to advertise another open source project that I've been working on. It's called Svalbard, and it's about backup of keys. So I guess this audience has lots of keys, lots of secret keys, maybe Bitcoin keys, and you probably want to, or you do backup them properly, but because you know how to do this. But I think the majority of people out there who also have maybe some secret keys, Bitcoin keys, they don't know how to do it. So the Svalbard system is trying to address this issue, and it's on GitHub. It's not a ready application yet. It's kind of base libraries, and it's kind of work in progress. But since it's open source, I would love to get some collaboration on that or criticism or whatever feedback. So it's on GitHub /Google/Svalbard, and Svalbard for the global seed vault that actually has also long-term backup of our civilization. So, okay, thank you very much.
Thank you. Nadia.
Hello, my name is Nadia Henninger. I like to break cryptography. I wanted to share a little bit of some of that joy with you. So some of you might know that the DSA signature scheme and also ECDSA are randomized, and it's very important to generate the random values carefully. And so in recent work that is now on ePrint, Joachim Breitner and I went and downloaded a bunch of cryptocurrency blockchains. We downloaded all of the signatures, and then we ran an attack, which actually I guess is partially due to Nigel Smart here. We basically used the algorithm lattice basis reduction. We ran it on all of the signatures in all of the blockchains that we downloaded, and we computed a bunch of private keys. It turns out that there's a bunch of vulnerabilities. Fun things like memory safety errors. We found an attacker who had a memory safety error in their nonce generation. We also found people who had used the wrong hash functions to generate their nonces, things like that. So if this kind of thing is fun to you, papers on ePrint. Thanks a lot.
Thank you. And, oops, no, reset. Go.
Hello, my name is Jeff Burgess. I work at the Web 3.0 Foundation, nothing to do with W3C. So we do various things and we're hiring, but the thing I wanted to say is we're organizing a sort of a discussion on meeting around mixed networking at the end of the month, sort of in proximity to FOSDEM in Brussels. So if you're interested in mixed networking, come chat with me.
Brilliant. Now, hold on a minute. We've got 3 people left. We've got about 15 minutes now. So you've got 5 minutes each, right?
Okay. Well, my name is Armando Faz. I'm working for Cloudflare right now. I want to try to invite you to this standardization effort about hashing to curve. So we know that many protocols are required to map arbitrarily strings to elliptic curve points. So there's a lot of mappings that are already published, but none of them all have like what are the proper mapping to use to these curves. So we're trying to do convey with what are the better algorithms, and we're happy to receive input and feedback from the community. So thank you so much.
Thank you very much. And go.
Hi, everybody. My name is Paul Grubbs. I'm a 4th-year PhD student at Cornell Tech, and I'd like to take the opportunity to announce some new results that just went up on ePrint. This is joint work with my co-authors Marie-Sarah Lacharité, Brice Minot, and Kenny Patterson. And the subject of this work is encrypted databases. So encrypted databases basically are useful if you want to outsource some data to an untrusted server, but still maintain the ability to do some queries and fetch the data. And most efficient, or all known efficient encrypted database schemes leak some information about the underlying data and the queries that you're making to make things more efficient. And in the academic community, a question that we've been asking in the last few years is kind of what the practical impact of this leakage is. And there, as Max kind of alluded to in his talk earlier, there have been some attacks that target specific leakages, but a kind of understanding of what this leakage is and what it can be used for different kinds of query classes is thus far eluded researchers. And in this paper, we start with the basic observation that access pattern leakage, which is leaked by all efficient encrypted database schemes, can be thought of as a kind of binary classification of the elements of the database. And using this observation, you can start to bring in techniques from learning theory, like epsilon nets and VC dimension, to kind of get very interesting, build very interesting theory that also lets you build practical attacks against encrypted databases. So the attacks in this paper are really cool, and they're also very practical, require very few queries, but they're also interesting because they kind of suggest a broader approach to understanding the security of efficient encrypted databases. So this is on ePrint now. If you're interested in machine learning, learning theory, applied cryptography, encrypted databases, or any of the intersections of those, it's 2019/011. So I urge you to check it out.
Just to drag the time out so you can't get a speech. Right, it's a pretty popular, this is kind of amazing. There's so many people here. Can you put your hand up if you have an open job at the moment that you're trying to recruit for? Right, so if you're a youngster, look how many jobs there are. It's amazing, yeah? So you are in a boom time. So, over to you. Have you got a job? Yes. Good, okay.
Hi, I'm Dionysis. I'm a PhD student at the University of Athens. I want to briefly announce a new result that we have with my co-authors, my advisor Agelos Keyas, who's here in the audience, and Peter Gaji from IOHK. We've been exploring the question of interoperability between blockchains, communicating information from one blockchain to another in a decentralized way. I know many of you may be interested in this question or are exploring it from a different point of view. I just want to allude to one specific part of our work, which is that we give a formal definition of what it means for a sidechain protocol to be secure. This is work that just went up on ePrint, so I invite you to go ahead and check it out and read it. The title is called Proof of Stake Sidechains, so you can Google that. And if you're in the Oakland conference, I'll be happy to have you also in the presentation of that paper there. Thank you.
Cool, thank you. And over to you.
Hi, I'm Benoît Viquier from Radboud University. I'm a PhD student there. Like every year, we're organizing, so we here are Real World Crypto, so every year we're organizing summer school on real world crypto and privacy. So if you feel like sending your students or spending a nice week in Croatia, feel free to come. It will be from the 11th of June to the 15th.
I think that was the shortest talk so far. Can you beat the shortest talk so far?
Good afternoon, or good morning still, I don't know, afternoon. My name is Tyler van der Merwe. I work for Mozilla in the security engineering team. I specifically work on crypto engineering. I've just been told that I should announce that we have an open position currently for a cryptography engineer, and we'll also be looking for someone in the next 6 months or so. So if you're interested, please come and talk to me. Thank you.
Before you head off for lunch, Brian wants to say something.
So I'm chairing for the next session. We're going to start at 2:10, so you guys have a little bit extra time for lunch. And with the speakers in the next session, please come up and meet me here right now when we break. Thanks.
And enjoy your lunch. And remember, there's an extra room over there if you want to sit down and do some other stuff. And big round of applause for everyone who gave up a bit of time to give you a talk. Thank you.